Welcome to the calmest coding journey you'll ever take. Get comfy, settle in, and let the gentle rhythm of this tutorial start to wash over you. Find a soft spot, maybe a cozy chair or a fluffy pillow. Breathe deeply, release any tension, and let the words flow like a lullaby. This is your time to relax, to learn, to unwind. As you watch, remember to like and subscribe for more soothing coding adventures. Happy coding and sweet dreams. Today we will explore the fundamentals of Swift and Xcode, the essential tools for developing applications on Apple platforms. We will begin by understanding the purpose of this session, which is to equip you with the foundational knowledge of Swift programming and the Xcode environment. The key topics we will cover include the unique features of the Swift language, how to navigate and utilize Xcode effectively, and the steps required to set up your development environment. By the end of this session, you will have clear learning objectives, such as writing your first Swift code and configuring Xcode for your projects. Let's dive in and build a strong foundation together. Swift is a modern programming language designed by Apple to deliver both performance and safety. It is specifically tailored for developing applications across all Apple devices, including iOS, macOS, watchOS, and tvOS. What makes Swift stand out is its ability to combine the speed of lower-level languages with the simplicity of higher-level ones. This means you can write efficient code without sacrificing readability. Additionally, Swift supports two major programming paradigms: object-oriented programming, which focuses on classes and objects, and functional programming, which emphasizes pure functions and immutability. This versatility allows developers to choose the approach that best suits their project's needs. Xcode is the Integrated Development Environment, or IDE, that Apple provides for building applications. It is a comprehensive toolset that includes everything you need to code, test, and deploy your apps. Within Xcode, you will find the Interface Builder, which allows you to design user interfaces visually, and Playgrounds, where you can experiment with Swift code in real time. The debugger is another crucial feature, enabling you to step through your code and inspect variables to identify and fix issues. Xcode also integrates with version control systems like Git, making collaboration on projects seamless. Whether you are writing code or testing your app, Xcode is your central hub for all development activities. To begin your journey with Xcode, you will first need to download it from the Mac App Store. Once downloaded, install the application and accept the license agreement to proceed. After installation, launch Xcode and take some time to configure your preferences, such as choosing a theme that suits your workflow or customizing keyboard shortcuts for efficiency. A critical step is verifying your installation by creating a new project. This will ensure that Xcode is set up correctly and that you can start developing apps without any issues. Let's walk through these steps to make sure your environment is ready for the next phase. Now, let's explore the basics of Swift syntax. One of the first concepts you'll encounter is the use of variables and constants. In Swift, variables are declared using the keyword var, which allows their values to change, while constants use let, which ensures their values remain fixed. Understanding data types is equally important. Swift includes types like int for integers, double for floating point numbers, string for text, bool for true or false values, and array for collections of elements. Comments are another essential tool, with for single-line comments and slash for multi-line explanations. Finally, the print function is used to output text or values to the console, making it a fundamental part of testing and debugging your code. The Xcode interface is designed to streamline your development process. The editor pane is where you write and modify your Swift code. The assistant editor allows you to view related files, such as storyboards or interface files, side by side, which is particularly useful when working on complex projects. The debug area provides a window into your app's runtime behavior, letting you inspect variables and step through your code line by line. Lastly, the navigator pane helps you manage your project files, set breakpoints, and review logs. Familiarizing yourself with these components will significantly enhance your productivity in Xcode. Writing and running code in Xcode begins with creating a new project. You can choose from various templates, such as the app template, which provides a starting point for building an application. When setting up your project, select Swift as the programming language and choose an interface style, such as Storyboard or SwiftUI, depending on your preference. Once the project is created, you will find the main code file, typically named View Controller Swift, where you can begin writing your logic. To test your app, use the simulator or connect a physical device and click the Run button to see your code in action. This process is the foundation of app development in Xcode. Let's look at some practical examples of Swift code. The first example is a simple print statement that displays a greeting. Print "Welcome to Swift." This is the most basic way to output information. Next, consider a calculation where we add two numbers. Let sum equals 5 plus 3. Here, let declares a constant, and the plus operator combines the values. Finally, a conditional statement checks if 10 is greater than 5 and prints a message if the condition is true. These examples illustrate how Swift handles basic operations and control flow, forming the building blocks for more complex programs. Xcode comes with several tools that enhance your development workflow. Playgrounds are an excellent way to experiment with Swift code interactively, allowing you to see results instantly without creating a full project. The debugger is invaluable for identifying and resolving issues by stepping through your code and inspecting variables at each stage. Version control integration with Git enables collaborative development, making it easier to track changes and work with others. Lastly, App Store Connect is the platform where you prepare and submit your apps for distribution, ensuring they meet Apple's guidelines and are ready for users to download. These tools are essential for a smooth development process. To wrap up, we've covered the essentials of Swift and Xcode. From understanding the language's features to setting up your development environment and writing your first code. Remember, practice is key to mastering these tools, so don't hesitate to experiment and explore Xcode's features further. In our next session, we will delve deeper into variables, data types, and control flow, expanding on the concepts introduced today. If you have any questions or need further clarification, feel free to ask. Happy coding, and let's continue building great applications together. A properly configured development environment is essential for any software development project. It ensures that your tools are optimized to handle the specific requirements of your work. For Swift development, you will need a few key tools. Xcode is the primary integrated development environment, and it includes everything you need to write, test, and debug Swift code. Other tools may include version control systems like Git and additional command line utilities. The objectives of this session are to guide you through installing Xcode, familiarizing yourself with its interface, and creating your first project. By the end, you will have a functional setup to begin writing Swift To begin, you will need to download Xcode from the Mac App Store or the official Apple developer website. Before proceeding with the installation, it is important to verify your system requirements. Your macOS version must be compatible with the latest Xcode release, and you should ensure you have sufficient disk space. Once the download is complete, open the installer and follow the prompts. After installation, you should check the Xcode preferences to install the command line tools. These tools are crucial for running Swift scripts outside the Xcode interface and for integrating with other development workflows. The Xcode interface is designed to streamline your workflow. The code editor is where you will write and edit your Swift code. It offers features like syntax highlighting and auto-completion to improve efficiency. The Assistant Editor allows you to view and compare multiple files side by side, which is helpful when working on complex projects. The debugger is a powerful tool for stepping through your code, inspecting variables, and identifying issues. Finally, the Navigator pane provides access to your project structure, helping you manage files, navigate through your code base, and access essential tools like the console and version control. Creating a new project in Xcode is straightforward. Start by opening Xcode and selecting the option to create a new project. You will be prompted to choose a template. For example, the app template is ideal for building iOS or macOS applications, while the command line tool template is suitable for scripts or utilities. Next, set a name for your project. Choose Swift as the programming language and specify a save location. Once the project is created, you will see the initial structure, including files like main Swift, which contains the entry point of your application, and info list, which stores configuration settings for your app. Configuring your project settings is a critical step in tailoring your development environment. Access the project settings through the Project Navigator, where you can adjust build settings such as the Swift version and deployment target. These settings ensure your code is compatible with the intended platform and tools. The info list file allows you to customize app capabilities, such as enabling camera access or setting up app icons. Additionally, setting up a scheme defines how your app runs, tests, and debugs. Schemes also let you configure different build configurations, like debug or release modes, to suit your development needs. During setup, you may encounter common issues that can hinder your progress. If Xcode does not open, check for updates or consider reinstalling the application. Swift version mismatches can cause compatibility problems, so use Xcode preferences to manage and switch between different Swift versions as needed. If your project fails to build, verify that file paths are correct and that all dependencies are properly linked. These troubleshooting steps will help you resolve most issues and ensure a smooth development experience. To recap, we have covered installing Xcode, understanding its interface, and creating your first project. A well-configured environment is the foundation of efficient Swift development, allowing you to focus on writing high-quality code. As you continue, I encourage you to practice with simple projects to reinforce your setup skills. Experimenting with different templates and configurations will deepen your understanding of Xcode and Swift, preparing you for more complex development tasks. Swift is a statically typed language, which means the type of every variable and constant is known at compile time. This helps catch errors early and ensures safer code. The language organizes code into statements, which are instructions that perform actions, and expressions, which are values that can be evaluated. For example, a statement might be a function call, while an expression could be a calculation. When declaring variables, we use the keyword var, which allows the value to change over time. For constants, we use let, which ensures the value remains fixed once assigned. Comments are an essential part of writing clear code, as they provide explanations for other developers or future reference. However, the compiler ignores comments entirely, so they don't affect the program's execution. Variables in Swift are declared using the var keyword, which makes them mutable. For instance, if we write var name equals Swift, we can later change the value of name to something else. On the other hand, constants are declared with let, making them immutable. An example would be let version equals 5, which cannot be modified after initialization. This distinction is crucial for writing predictable and safe code. Swift also supports type inference, which means the compiler can automatically determine the data type based on the assigned value. For example, if we assign a string to a variable, the compiler knows it's a string without needing an explicit declaration. This feature reduces redundancy and makes code more concise. Swift offers several common data types, including integers, floating point numbers, strings, Boolean values. Integers, represented by int, can store whole numbers like 42 or 0b1010, which is a binary literal. Floating point numbers, such as double, handle decimal values like 3.14 or 1.23e4, which uses scientific notation. Strings are used to store text and can be written as hello, world, or as multi-line strings using triple quotes. Boolean values, denoted by bool, represent true or false and are essential for decision-making in programs. Understanding these types helps developers choose the right structure for their data and ensures efficient memory usage. Operators in Swift allow us to perform operations on values. Arithmetic operators like plus, minus, multiplication, and division manipulate numerical data. Comparison operators such as equals, not equals, greater than, and less than help evaluate relationships between values. Logical operators like and, or, and not are used to combine conditions, enabling complex decision-making. The assignment operator, which is equals, is different from equality, a common source of confusion. For example, using equals to assign a value is distinct from checking if two values are equal. Mastery of these operators is fundamental for writing dynamic and responsive code. Comments in Swift are a vital tool for improving code readability and documentation. Single-line comments start with 2 forward slashes, while multi-line comments are enclosed in slash and asterisk pairs. These comments help explain the purpose of code sections, making it easier for others to understand and maintain. However, it's important to avoid over-commenting, especially when the code itself is self-explanatory. Well-placed comments can clarify complex logic or note important decisions, but they should never be used to repeat what the code already says. Proper code structure and indentation are critical in Swift for readability and maintainability. The language uses white space to separate elements, and consistent indentation, typically 4 spaces, helps visualize the flow of code. Functions and control structures, such as if statements or loops, use braces to define blocks of code. For example, an if statement might look like this: if true, print condition met, even though Swift doesn't require semicolons. The structure of the code must be clear to prevent errors. A well-organized code base is easier to navigate and less prone to bugs. In conclusion, This presentation has covered the essentials of Swift programming. We explored variables and constants, learning how to declare mutable and immutable values. We examined data types and literals, understanding how to represent different kinds of information. Operators and expressions were discussed, highlighting their role in performing calculations and making decisions. Comments and code structure were emphasized as tools for clarity and maintainability. By practicing these concepts, developers can write clean, readable Swift code that is both efficient and easy to work with. Continued practice will solidify these foundations for more advanced programming tasks. Variables are essential tools in Swift programming that allow you to store and manage values that can change during the execution of a program. For example, if you are building an app that tracks a user's score in a game, the score would be stored in a variable because it updates as the game progresses. On the other hand, constants are used for values that remain fixed once assigned, such as the number of seconds in a minute or a fixed configuration setting. Both variables and constants play a critical role in organizing data in your code. By using them appropriately, you can make your code more readable as it becomes easier to understand what data is intended to change and what is meant to stay the same. This distinction also enhances code safety, as constants prevent accidental modifications that could lead to bugs. To declare a variable in Swift, you use the keyword var followed by the variable name and an initial value. For instance, var age equals 25 creates a variable called age with the value 25. One of the key features of variables is that they can be reassigned later in the code. For example, after initializing age as 25, you could later write age equals 26 to update its value. Swift has a powerful feature called type inference, which means it automatically determines the data type of a variable based on the value you assign. In the example, age is inferred as an integer because 25 is a whole number. This reduces the need for explicit type declarations and makes the code more concise. However, there are cases where you might need to specify the type manually, which we will discuss in later slides. Constants are declared using the keyword let, which stands for let, as in let it be. For example, let name equals Alice creates a constant called name with the value Alice. Unlike variables, constants cannot be modified after they are initialized. If you attempt to assign a new value to a constant, Swift will generate a compile time error, which stops the program from running until the issue is fixed. This feature is particularly useful for values that should never change, such as mathematical constants like the value of pi or configuration settings in an app. By using constants, you ensure that certain values remain consistent throughout the program, which can prevent unexpected behavior and make your code more reliable. When naming variables and constants in Swift, it is important to follow specific conventions to ensure clarity and avoid errors. First, use descriptive names that clearly indicate the purpose of the variable or constant. For example, instead of naming a variable x, use username or total price to make its role obvious. Swift uses camel case, where the first letter of each word after the first is capitalized, such as username. Avoid using reserved keywords like var, let, or if as names, as this can cause syntax errors. Additionally, names must start with a letter or an underscore, and Swift is case sensitive, meaning age and age are considered different identifiers. Following these rules helps prevent naming conflicts and makes your code easier to read and maintain. Swift's type inference system allows the compiler to deduce the data type of a variable or constant based on the value you assign. For example, if you write var count equals 10, Swift automatically infers that count is an integer because 10 is a whole number. This feature simplifies code by reducing the need for explicit type declarations. However, there are situations where type inference might not be sufficient or could lead to ambiguity. For instance, if you write var pi equals 3.14, Swift might infer it as a double. But if you need to ensure it is a specific type, you can add an explicit type annotation. This is done by writing var pi double equals 3.14. Explicit typing is particularly useful when the value could be interpreted in multiple ways, such as a string that looks like a number, while type inference makes code cleaner. It is important to balance it with explicit declarations to avoid confusion in complex scenarios. The choice between variables and constants in Swift revolves around mutability and immutability. Variables declared with var are mutable, meaning their values can be changed after initialization. This makes them suitable for data that evolves during program execution, such as a user's score in a game or the current time. Constants declared with let are immutable, meaning their values cannot be altered once set. This is ideal for values that should remain fixed, such as the number of days in a week or a fixed API endpoint. Using let by default whenever possible can lead to safer code, as it prevents unintended changes. However, when a value needs to be updated, var is the correct choice. Understanding when to use each ensures that your code is both efficient and easy to debug. Adhering to best practices when working with variables and constants can significantly improve the quality of your Swift code. First, always prefer let over var unless you explicitly need mutability. This reduces the risk of accidental changes and makes your code more predictable. Second, avoid naming conflicts by ensuring your variable and constant names do not clash with reserved keywords or other identifiers in your code. Third, use meaningful names that clearly describe the purpose of the data, which makes your code more readable for others and for your future self. Finally, always initialize variables and constants with appropriate values to ensure they are ready for use. These practices contribute to writing clean, maintainable, and efficient Swift programs. In summary, variables and constants are foundational elements in Swift programming that enable you to manage data effectively. Variables declared with var are used for values that can change, while constants declared with let are used for values that remain fixed. Proper naming conventions and type declarations enhance code clarity and prevent errors. By understanding the difference between mutability and immutability, you can write safer and more reliable code. Applying these principles in your projects will help you build efficient, maintainable programs that are easier to read and debug. As you continue learning Swift, practice using both variables and constants to reinforce these concepts and improve your coding skills. Data types define the kind of data a variable or constant can hold. In Swift, this is crucial because it determines how data is stored and manipulated in memory. Swift is a statically typed language, which means the type of every variable and constant is known at compile time. This approach allows the compiler to catch errors early, before the code even runs. Common data types include integers, floating point numbers, text, Boolean values, and collection types like arrays and dictionaries. Choosing the right type ensures that your program uses memory efficiently and avoids unexpected errors. For example, using an integer type for whole numbers prevents issues that might arise from trying to store decimal values in a variable meant for integers. Type inference allows Swift to automatically determine the type of a variable or constant based on the value assigned to it. For instance, when you write let number equals 42, the compiler recognizes that 42 is an integer and infers the type as int. This feature reduces the need for redundant type declarations, making code cleaner and easier to read. Type inference works best when you assign a value immediately upon declaration. It's a powerful tool that streamlines development while maintaining the benefits of static typing. However, it's important to note that if a variable is declared without an initial value, you must specify its type explicitly. Type safety ensures that variables and constants hold only the correct type of data, preventing unintended operations. This is a core principle of Swift, as it helps avoid runtime errors that can occur when, for example, a string is mistakenly assigned to a numeric variable. The compiler enforces these rules during compilation, ensuring that your code adheres to strict type constraints. For instance, if you define a variable as a string, trying to assign a number to it will result in a compile time error. This proactive approach to error prevention makes Swift programs more reliable and easier to debug. Swift offers several basic data types that form the foundation of data handling. Integers, represented by the int type, store whole numbers and come in various sizes like int 8, int 16, int 32, and int 64, depending on the range of values needed. Floating point numbers, such as double and float, handle decimal values, with double providing higher precision for scientific calculations. Strings store text data like hello and are essential for handling user input or displaying messages. Boolean values, true or false, are used for logical operations and condition checks. Understanding these types helps you structure your data effectively and optimize performance. Type inference in action demonstrates how Swift simplifies code by deducing types from assigned values. For example, when you write let pi equals 3.14159, the compiler infers this as a double because of the decimal point. Similarly, let is raining equals false becomes a bool type. For collections like arrays, if you assign let fruits equals apple, banana, the compiler recognizes this as an array of strings. This capability not only reduces boilerplate code, but also makes the code more readable. However, type inference works only when a value is explicitly provided at declaration. So it's important to understand its limitations. Explicit type annotations allow you to specify the type of a variable or constant directly. This is done using a colon followed by the type, such as let's score int equals 100, which forces the variable to be an integer. This practice is particularly useful when the initial value is ambiguous, or when you want to override the compiler's inference. For example, if you have a number that could be an int or a double, specifying the type ensures clarity. Explicit annotations also improve code readability in complex scenarios, making it easier for others to understand your intentions without relying solely on type inference. Complex data types in Swift include arrays, dictionaries, and tuples, which allow you to organize and manage multiple values. Arrays store ordered collections of elements, such as int for a list of integers. Dictionaries use key-value pairs, like string, int, to map unique keys to corresponding values. Tuples group multiple values into a single compound value, such as int, string to hold a number, and a name. Type inference works seamlessly with these structures, as the compiler can determine their types based on the assigned values. This flexibility makes complex data handling more intuitive and efficient. Type conversion in Swift requires explicit steps to ensure data integrity. Unlike some languages that allow implicit conversions, Swift mandates that you manually convert between types. For example, converting an integer to a double requires let y equals doublets, where x is an int. This approach prevents accidental data loss, such as truncating a decimal value when converting to an integer. Swift provides functions like int, double, and string to perform these conversions, ensuring that each operation is intentional. By enforcing explicit conversions, Swift maintains type safety and reduces the risk of unexpected behavior. Data types define the structure and behavior of data in your programs, making them fundamental to any Swift application. Type inference simplifies code by automating type detection, while type safety ensures that your variables and constants behave as expected. Combining these concepts leads to robust, error-free code that is easier to maintain and debug. Mass mastering data types, inference, and conversion is essential for writing efficient and reliable Swift programs. Whether you're building simple apps or complex systems, a solid understanding of these principles will enhance your development workflow and improve the quality of your code. Operators perform actions on operands, which are values or variables. Expressions combine these values, variables, and operators to produce a result. These elements are essential for building logic, comparisons, and calculations in the Swift programming language. Understanding how to use operators and expressions allows developers to create dynamic and responsive applications by manipulating data and making decisions based on conditions. Swift includes several types of operators. Arithmetic operators such as plus, minus, multiplication, division, and modulo perform mathematical operations. Comparison operators like equal to, not equal to, greater than, less than, greater than or equal to, and less than or equal to are used to compare values. Logical operators such as not and or help in combining Boolean conditions. Assignment operators like equals, plus equals, minus equals, multiply equals, and divide equals allow for setting and updating variable values. The ternary operator is a shorthand for conditional expressions. Each of these operators plays a critical role in writing efficient and readable code. Arithmetic operators handle basic operations like addition, subtraction, multiplication, and division. The modulo operator returns the remainder of a division operation. For example, adding 5 and 3 results in 8, while dividing 10 by 3 leaves a remainder of 1. These operators are fundamental for performing calculations in any program, whether it's computing financial figures, game scores, or scientific data. Mastery of arithmetic operators enables precise control over numerical computations. Comparison operators are used to compare values and return a Boolean result, which is either true or false. For instance, checking if a variable is equal to another value, or if one value is greater than another, is essential for making decisions in code. These operators are the building blocks of conditional statements, allowing programs to execute different code paths based on specific criteria. Examples include checking if a user's input meets a certain condition, or validating data against predefined rules. Logical operators are used to combine or invert Boolean values. The not operator inverts a Boolean value. The and operator returns true only if both operands are true, and the or operator returns true if at least one operand is true. These operators are crucial for creating complex conditions, such as checking if a user is both logged in and has the necessary permissions. By combining logical operators, developers can craft intricate decision-making logic that adapts to different scenarios. Assignment operators are used to assign values to variables. The basic equals operator sets a variable to a specific value, while compound operators like plus equals, minus equals, multiply equals, and divide equals combine assignment with arithmetic operations. For example, incrementing a counter by 2 using plus equals simplifies the code compared to writing it out explicitly. These operators enhance code readability and reduce the potential for errors by minimizing repetitive code. Expressions in Swift are combinations of values, variables, and operators that evaluate to a single result. They can range from simple operations like adding 2 numbers to complex conditions involving multiple variables and logical checks. For example, multiplying the sum of 2 variables by a third creates a more intricate expression. Expressions are the foundation of programming logic, enabling developers to perform calculations and make decisions dynamically. Operator precedence determines the order in which operations are performed in an expression. For example, multiplication is evaluated before addition unless parentheses dictate otherwise. Associativity defines how operators of the same precedence are grouped, either from left to right or right to left. Understanding these rules is vital for writing correct code, as incorrect precedence can lead to unexpected results. Parentheses are a powerful tool for explicitly defining the order of operations, ensuring clarity and preventing errors. Common operator examples illustrate their practical use. Arithmetic operators like multiplication are used to calculate areas or totals. Logical operators combine conditions, such as checking if it is sunny and the temperature is above a certain threshold. The ternary operator provides a concise way to assign values based on a condition, such as determining a status message. These examples demonstrate how operators and expressions are integral to solving real-world problems efficiently. Operators and expressions are fundamental crucial for manipulating data and making decisions in Swift. Understanding their types, precedents, and usage ensures that code is both functional and readable. By practicing with operators, developers can build complex logic and create efficient programs that handle a wide range of scenarios. Continuous practice and experimentation with these concepts are key to mastering Swift and becoming a proficient programmer. Control flow is the foundation of decision-making in programming. It allows our code to execute different blocks of logic based on specific conditions or values. This is essential for creating dynamic and responsive applications. The two primary constructs we use are if else for conditional branching and switch for pattern matching. If else lets us evaluate a condition and choose between two or more paths, while switch allows us to compare a value against multiple possible patterns. These tools are crucial for handling different scenarios, such as user input, variable states, or complex business logic. Understanding control flow is the first step in writing efficient and readable Swift code. The if else structure is one of the most fundamental ways to control the flow of a program. When we use if, we check a condition, and if that condition is true, the code inside the if block runs. If the condition is false, the else block provides an alternative set of instructions. For example, if we check the temperature, we can print a message indicating whether it is a hot day or mild weather. This simple structure allows us to make decisions based on the current state of our program. It is important to note that in Swift, the condition must evaluate to a Boolean value, and the code blocks are enclosed in curly braces. When we have more than two possible conditions, we can use else if to check additional scenarios. This allows us to create a chain of conditions that are evaluated in order. For instance, if we are grading a test, we can check if the score is above 90 for an A, then 80 for a B, and so on. Nested conditions take this further by allowing us to place if else statements inside other if else blocks. This is useful for handling more complex decision trees, such as validating multiple user inputs or processing different layers of data. However, it is important to keep nested conditions manageable to avoid confusing code. Switch statements offer a powerful alternative to if else when we need to match a value against multiple possibilities. Unlike some other languages, Swift requires that all possible values are covered in a switch statement, ensuring no cases are missed. This makes our code more robust and less prone to errors. For example, if we are checking the day of the week, we can define a case for each day and a default case for any unexpected values. Switch statements are particularly useful when dealing with enums or when the data has a finite set of known values. They also support more advanced patterns, which we will explore in the next slides. Switch cases can go beyond simple equality by using patterns such as ranges, tuples, and value bindings. A range like 1, 5 can match any integer within that span, making it easy to handle groups of values. Tuples allow us to match combinations of values, such as checking if a point is on the x-axis or origin. Value bindings let us extract and use specific parts of a case, which is helpful when we need to work with the matched data. For example, if we have a coordinate pair, we can bind x and y values to perform further calculations. These features make switch statements incredibly versatile for handling complex data structures. Every switch statement must include a default case to handle any values that do not match the defined cases. This ensures that our code is exhaustive and avoids runtime errors. In Swift, the default case is mandatory unless all possible values are explicitly covered. Another unique feature is fall-through, which allows the code to continue executing the next case after a match. However, fall-through is optional and should be used sparingly, as it can lead to unexpected behavior if not managed carefully. While fall-through is not commonly used in Swift, it can be useful in specific scenarios where multiple cases need to share the same code. Choosing between if else and switch depends on the situation. If else is ideal for complex conditions that involve logical operators or overlapping ranges. For example, checking if a number is greater than 10 but less than 20 is easier with if else. Switch, on the other hand, excels at handling exact matches and patterns, such as checking for specific enum values or tuple combinations. Switch also enforces exhaustive matching, which reduces the risk of missing cases. However, if else offers more flexibility when dealing with conditions that are not mutually exclusive. Understanding when to use each construct is key to writing clear and efficient Swift code. In summary, control flow is the backbone of decision-making in programming. By mastering if else and switch, we can create code that adapts to different situations and data. If else is perfect for branching logic with complex conditions, while switch is great for pattern-based decisions and exhaustive matching. Practicing these constructs will help you solve real-world problems more effectively. As you continue learning Swift, remember to choose the right tool for the task and always consider readability and maintainability. With practice, you will become proficient in crafting dynamic and responsive applications. Loops are fundamental tools in programming that allow us to execute a block of code multiple times. This is especially useful when we need to perform repetitive tasks without writing the same code over and over again. In Swift, there are 3 primary types of loops: for while and repeat while. Each of these loops serves a specific purpose and can be used to handle different scenarios. For example, a for loop is ideal when we know the number of iterations in advance, while a while loop continues executing as long as a certain condition remains true. The repeat while loop, on the other hand, ensures that the code inside the loop runs at least once before checking the condition. Understanding these loops is essential for writing efficient and readable code in Swift. The for loop in Swift is designed to iterate over a sequence, such as a range of numbers or elements in an array. The syntax for a for loop is straightforward. We define a variable that takes on each value in the range, and then we write the code we want to execute. For instance, if we write for I in 1 through 5, the loop will run 5 times, with the variable I taking the values 1, 2, 3, 4, and 5. This makes the for loop particularly useful when we need to perform an action a specific number of times, or when working with collections like arrays, dictionaries, or sets. It's also important to note that in Swift, ranges can be closed, such as 1, 5, which includes both the start and end values, or half open, like 1, 5, which stops before the end value. This flexibility allows developers to tailor their loops to the exact needs of their programs. The while loop in Swift is used when we want to execute a block of code repeatedly as long as a certain condition remains true. The syntax for a while loop is simple. We start with the keyword while, followed by a condition in parentheses, and then the code block in curly braces. For example, if we initialize a variable I to 1 and write a while loop that checks if I is less than or equal to 5, the loop will run as long as that condition holds. Each time the loop runs, we increment I by 1, ensuring that the condition eventually becomes false and the loop stops. However, it's crucial to remember that if the initial condition is false, the loop will not execute at all. This makes the while loop ideal for situations where the number of iterations is not known in advance, but depends on dynamic data or user input. The repeat while loop, also known as a do while loop in some other programming languages, is unique because it guarantees that the code inside the loop will execute at least once before the condition is checked. The syntax for this loop starts with the keyword repeat, followed by the code block in curly braces, and then the while keyword with the condition. For example, if we initialize I to 1 and write a repeat while loop that checks if I is less than or equal to 5, the loop will run once, increment I, and then check the condition again. This structure is particularly useful when we need to perform an action at least once, regardless of the condition, and then continue based on the result. It's often used in scenarios like user input validation, where we want to prompt the user at least once before checking their response. When choosing between the 3 types of loops, it's important to consider the specific requirements of the task at hand. The for loop is best suited for iterating over a known range or collection, such as a sequence of numbers or elements in an array. It provides a concise and readable way to handle predictable iterations. The while loop, on the other hand, is ideal when the number of iterations depends on a condition that may change during the program's execution. However, it's possible for the while loop to not run at all if the initial condition is false. The repeat while loop is the only one that guarantees the code block runs at least once, making it perfect for situations where the condition is not known until after the first iteration. Understanding these distinctions allows developers to select the most appropriate loop for their specific needs, leading to more efficient and maintainable code. In conclusion, loops are a cornerstone of programming in Swift, enabling developers to automate repetitive tasks and streamline their code. Whether it's a for loop for iterating over a sequence, a while loop for dynamic conditions, or a repeat while loop for guaranteed execution, each type has its place in the developer's toolkit. The key to mastering loops is practice, experimenting with different scenarios, debugging common issues like infinite loops, and learning to recognize the best use cases for each loop type. By applying loops to real-world problems, such as processing data, managing user interactions, or building algorithms, programmers can unlock the full potential of Swift and create more powerful, efficient applications. Closures are powerful constructs in Swift that allow you to encapsulate a piece of functionality and pass it around like a value. They are essentially blocks of code that can be stored, passed as arguments, or even returned from functions. What makes closures particularly useful is their ability to capture and store references to constants and variables from the surrounding context in which they are defined. This means a closure can access and modify values from its environment, even if those values are no longer in scope. Unlike functions, which require a name and a separate declaration, closures can be written inline and often in a more concise manner. They are widely used in Swift for tasks such as sorting, filtering, and transforming data, making your code more expressive and efficient. By leveraging closures, you can write cleaner and more modular code that is easier to read and maintain. The syntax for closures in Swift is designed to be both flexible and expressive. At its core, a closure is written using curly braces, followed by a parameter list, an arrow indicating the return type, and the body of the closure. For example, a closure that takes two integers and returns their sum would be written as x, int y, int in return x plus y. However, Swift can often infer the return type based on the closure's body, so you can omit it if it's clear from the context. Parameters can also be referenced by their position using $0, $1, and so on, or by name if you choose to specify them. This flexibility allows you to write closures that are both readable and compact. Whether you're defining a simple operation or a complex logic block, the closure syntax adapts to your needs while maintaining clarity. Understanding this structure is essential for effectively using closures in your Swift projects. One of Swift's most useful features is the ability to write trailing closures, which are closures that appear after a function's parentheses when they are the last parameter. This is particularly common in higher order functions like map, filter, and sorted, where the closure is the final argument. For instance, instead of writing array map $0 times 2, you can simplify it to array.map $0 times 2, which improves readability by reducing visual clutter. Trailing closures make the code more concise and easier to follow, especially when the closure is long or involves multiple lines of logic. This syntax is a hallmark of Swift's design philosophy, prioritizing clarity and reducing boilerplate code. By using trailing closures, you can focus more on the logic itself rather than the syntactic structure, making your code more elegant and maintainable. Swift provides shorthand argument names to make closures even more concise, especially when the parameters are simple and the closure is short. These names are automatically assigned as $0, $1, $2, and so on, corresponding to the order of the parameters. For example, numbers filter $0 greater than 5 is a compact way to express a closure that checks if a number is greater than 5. This feature is particularly handy for quick operations, where explicitly naming parameters would add unnecessary complexity. However, while shorthand names improve brevity, they can sometimes reduce clarity in more complex closures. It's best to use them for simple logic where the context is clear, and to name parameters explicitly when the closure's purpose might be less obvious. This balance between conciseness and readability is key to writing effective Swift code. Closures have the unique ability to capture values from their surrounding context, which means they can access and store references to constants and variables defined outside their own scope. For example, if you define a multiplier constant and then create a closure that multiplies a number by that constant, the closure will retain a reference to the multiplier. This is incredibly powerful, but comes with a caveat. If the closure captures a strong reference to a class instance, it can create a retain cycle, where two objects hold strong references to each other and never get deallocated. To avoid this, you should use weak or unowned references when capturing self or other instances that might be deallocated. Understanding how closures capture values is crucial for writing efficient and memory-safe Swift code, especially in complex applications with multiple interconnected objects. In Swift, closures can be either escaping or non-escaping, depending on how they are used. A non-escaping closure is the default and is typically used for synchronous operations where the closure is executed immediately. For example, a closure passed to a function that processes data right away is non-escaping. However, if a closure is stored and called later, such as in an asynchronous task or a completion handler, it must be marked with the @escaping keyword. This tells Swift that the closure may outlive the function that creates it, requiring careful management of memory to avoid leaks. Escaping closures are common in scenarios like network requests or animations, where the closure is executed after the function has returned. By understanding the difference between escaping and non-escaping closures, you can write more robust and efficient code that adheres to Swift's safety guarantees. In summary, closures are one of the most versatile and essential features of Swift, enabling you to write concise, expressive, and reusable code. From their flexible syntax to their ability to capture values from their environment, closures offer a powerful way to handle complex logic with minimal boilerplate. Trailing closures improve readability. Shorthand argument names enhance brevity, and understanding escaping versus non-escaping closures ensures safe memory management. By practicing with higher-order functions like map, filter, and sorted, you can unlock the full potential of closures in your projects. As you continue to explore Swift, remember that mastering closures will not only make your code more efficient, but also make you a more proficient and confident developer. Arrays are a fundamental data structure in Swift that allow you to store multiple values of the same type in an ordered collection. Think of an array as a list where each item has a specific position, starting from 0. This means the first element is at index 0, the next at index 1, and so on. Arrays can be either immutable, which means their contents cannot change once created, or mutable, which allows you to add, remove, or modify elements. For example, if you create an array called numbers with values 1, 2, and 3, you can later update one of those values or add new numbers to the array. This flexibility makes arrays ideal for situations where you need to manage a sequence of data that may change over time. Creating arrays in Swift can be done in several ways. The simplest method is using array literals, where you list the elements inside square brackets. For instance, a list of names like Alice and Bob can be written as Alice, Bob. If you need an array with repeated values, such as 5 zeros, you can use the repeating initializer, which takes a value and a count. Another way to build arrays is by appending elements one by one using the append method or the plus equals operator. Additionally, you can convert other collections, like sets or ranges, into arrays using the array initializer. These methods provide versatility when initializing arrays for different use cases. Accessing elements in an array is straightforward because each element has a unique index. For example, if you have an array of names the first name is at index 0, the second at index 1, and so on. You can modify an element by assigning a new value to its index, such as changing the second name in the array to Charlie. To check how many elements are in an array, you can use the count property, which returns an integer. If you need to determine whether an array is empty, the isEmpty property returns a Boolean value. These tools help you manage and interact with arrays effectively in your code. Swift provides several built-in methods to manipulate arrays. The append method adds a single element to the end of the array, while the remove method deletes an element at a specific index. If you want to insert an element at a particular position, the insert method allows you to do so. Another useful method is sorted, which returns a new array containing the elements in ascending order without modifying the original array. These methods give you powerful ways to modify and organize your data, making arrays a flexible tool for handling dynamic collections of information. Dictionaries are another essential data structure in Swift, designed to store key-value pairs. Each key in a dictionary must be unique and hashable, which means it can be used to quickly look up its corresponding value. Common hashable types include strings, integers, and custom types that conform to the hashable protocol. For example, a dictionary might map names to ages, where Alice is the key and 30 is the value. Unlike arrays, dictionaries do not maintain a specific order, making them ideal for scenarios where you need to retrieve data based on a specific key rather than an index. Creating dictionaries in Swift can be done using dictionary literals, where you list key-value pairs inside curly braces. For instance, a dictionary of scores might look like math, 90, science, 85. If you need an empty dictionary, you can initialize it with string int, specifying the types of the keys and values. The dictionary initializer is another option, which can improve clarity when creating dictionaries with specific types. Additionally, you can convert an array of key-value tuples into a dictionary using the dictionary initializer, which is useful when working with data that needs to be restructured. Accessing values in a dictionary is done using their corresponding keys. For example, if you have a dictionary called scores, you can retrieve the value for math by writing scores math. Since a key might not always exist, this returns an optional value, which you can safely unwrap using if-let or guard-let. To update a value or add a new key value pair. The update value method is useful because it either updates the existing value or inserts a new one if the key is not present. Checking for the existence of a key can be done using the contain swear method or by directly checking if the optional value is not nil. Dictionaries offer several methods to manage their contents. The remove value of a key method deletes a key value pair from the dictionary, which is helpful when you no longer need specific data. The keys and values properties return collections of all the keys or values in the dictionary, allowing you to iterate over them or perform operations like filtering. The isempty property checks if the dictionary has no entries, while the count property returns the total number of key value pairs. These tools make it easy to inspect and manipulate dictionaries in your code. Arrays and dictionaries serve different purposes in Swift. Arrays are ordered and use integer indices to access elements, making them suitable for sequences like lists or queues. Dictionaries, on the other hand, are unordered and use keys to retrieve values, making them ideal for lookups like phone books or configuration settings. Arrays allow duplicate elements, while dictionaries require unique keys. When deciding between the two, consider whether you need to maintain order or access data by a specific identifier. Understanding these differences helps you choose the right data structure for your specific needs. In conclusion, arrays and dictionaries are indispensable tools for managing collections of data in Swift. Arrays are perfect for ordered sequences, while dictionaries excel at key-based lookups. Mastering methods like append, remove, and key value operations will enhance your ability to work with these structures effectively. Practicing with real-world examples, such as managing a list of tasks or a database of user information, will solidify your understanding and help you apply these concepts in practical scenarios. By leveraging the strengths of arrays and dictionaries, you can write more efficient and organized code. Sets are unordered collections of unique elements, which means they do not maintain any specific order for their contents. This makes them different from arrays, which are ordered and allow duplicates. In Swift, the set type ensures that every value stored within it is unique, automatically removing any duplicates you might attempt to add. This characteristic makes sets particularly useful when you need to check for the presence of an element quickly, such as verifying if a value exists in a group. Additionally, sets are great for performing mathematical set operations like combining, intersecting, or comparing collections. Since they don't track order, they are ideal for scenarios where the sequence of elements doesn't matter, but uniqueness and efficient lookups do. To create a set in Swift, you can use the set element initializer or directly initialize it with an array literal. For example, you might write let numbers set equals 1, 2, 3 to create a set of integers. Swift's type inference allows for shorthand notation, so you can declare a set without explicitly specifying the type, like var names equals Alice, Bob, and the compiler will infer it as a set. Another way to initialize a set is by using the set array literal initializer, which is helpful when converting an array into a set to remove duplicates. This flexibility makes it easy to work with sets in various contexts, whether you're starting from scratch or converting existing data structures. Set operations in Swift allow you to manipulate collections in powerful ways. The union operation combines elements from two sets, creating a new set that contains all unique values from both. The intersection operation finds elements that are present in both sets, which is useful for identifying commonalities. The symmetric difference operation includes elements that are in either set, but not in both, effectively excluding overlaps. Lastly, the subtraction operation removes elements found in another set, leaving only the unique elements from the original set. These operations mirror mathematical set theory and are essential for tasks like merging data, finding overlaps, or filtering out specific values. Checking membership and equality in sets is straightforward. The contains method allows you to verify if an element exists within a set, which is typically faster than checking in an array due to the underlying hash table implementation. You can also use isEmpty to determine if a set has no elements and count to find out how many elements it holds. For comparing sets, methods like isSubsetOf check if all elements of one set are in another, isSupersetOf does the opposite and is disjoint with, confirms if two sets share no common elements. These tools are invaluable for logical comparisons and ensuring data integrity in your programs. Iterating through a set is done using a for-in loop, which allows you to access each element. However, it's important to note that the order of elements in a set is not guaranteed. Unlike arrays, which maintain a specific sequence, sets can return elements in any order, depending on how the underlying data structure is organized. This means that if you need a predictable sequence, a set may not be the right choice. For example, when printing elements of a set, the output might vary each time you run the code. Still, for tasks where order isn't important, this feature makes sets efficient and versatile. Sets support collection operations that let you filter, map, and reduce their contents. Filtering allows you to create a new set by including only elements that meet a specific condition, such as selecting even numbers from a set of integers. Mapping transforms each element in a set, though the resulting values must still be unique to maintain the set's properties. Reducing aggregates elements into a single value, like summing all numbers in a set. These operations are powerful for processing data and can simplify complex logic, making your code more concise and readable. Sets are incredibly useful in practical scenarios where uniqueness and efficient operations are critical. For instance, they are ideal for managing unique identifiers like user IDs, ensuring no duplicates exist in a system. In graph algorithms, sets can track visited nodes to prevent cycles or repeated processing. Another common use is removing duplicates from an array by converting it to a set and then back to an array. These applications highlight how sets can streamline data management, improve performance, and reduce the risk of errors in your code. When working with sets, there are a few common pitfalls to avoid. First, remember that sets are unordered, so relying on the sequence of elements can lead to unexpected behavior. Misusing the equality operator equals might also cause issues if you're not aware of how it compares set values. Finally, not leveraging set operations can result in less efficient code, as built-in methods are optimized for performance. By understanding these challenges, you can use sets more effectively and avoid potential bugs in your programs. In conclusion, sets provide an efficient way to store and manipulate unique values, offering powerful operations that enhance code clarity and performance. By mastering set operations, you can handle tasks like membership checks, mathematical comparisons, and data transformations with ease. Applying sets in scenarios that require uniqueness or logical set operations can lead to cleaner, more efficient code. Whether you're managing identifiers, optimizing algorithms, or simplifying data processing, sets are a valuable tool in your Swift programming toolkit. Strings are used to represent text in Swift. They are fundamental for handling textual data in applications, whether it's displaying messages, processing user input, or storing information. Characters, on the other hand, are individual units of text, such as letters, numbers, or symbols. Each character in a string is a distinct element, and together they form the complete string. Both strings and characters are value types in Swift, which means that when you assign or pass them to a function, a copy is made rather than a reference. This behavior ensures predictable and safe operations, especially when dealing with mutable data. Swift leverages Unicode to support a wide range of languages and scripts, making it ideal for internationalization. This means your code can handle text in any language, including complex scripts like Arabic or Chinese, as well as emojis and special characters. To create strings in Swift, you can use string literals, which are simply text enclosed in double quotes. For example, let greeting equals hello world creates a string containing the phrase hello world. If you need an empty string, you can initialize it with an empty pair of double quotes, like var empty string equals. Alternatively, you can use the string initializer, which is particularly useful when converting other types to strings. For instance, let empty equals string creates an empty string, while string 42 converts the integer 42 into the string 42. This flexibility allows you to build strings dynamically, whether you're starting with a blank slate or converting numerical values into human-readable text. String concatenation in Swift is straightforward. You can use the plus operator to combine multiple strings, such as let combined equals hello plus plus world, which results in hello world. Another powerful technique is string interpolation, where you embed expressions directly within a string. For example, if you have a variable name equals Alice, you can create a message like hello $name to produce hello Alice. This is especially useful when dynamically generating text based on variables or calculations. Additionally, you can append to existing strings using the plus equals operator. For instance, if you have a greeting equals hello, you can add world to it by writing greeting plus equals world. These methods provide versatile ways to build and modify strings efficiently. Strings in Swift have several properties and methods that allow you to inspect and manipulate their contents. For example, the count property gives you the number of characters in a string, while isEmpty checks if the string is empty. You can also use hasPrefix and hasSuffix to determine if a string starts or ends with a specific substring. When it comes to modifying strings, methods like uppercased and lowercased convert the string to uppercase or lowercase, respectively. The replace occurrences off with method lets you replace specific parts of a string, making it easy to clean or transform text. These tools are essential for tasks like validating input, formatting data, or preparing text for display. Each string is composed of individual characters, and Swift provides ways to access and work with them. For example, you can loop through a string's characters using a for-in loop, allowing you to process each character one by one. If you need to work with characters as a collection, you can convert the string into an array of characters. This is useful for tasks like counting specific characters or rearranging the order of characters in a string. Understanding how to handle characters is crucial when dealing with text that requires per character operations, such as encryption, parsing, or custom formatting. By treating a string as a sequence of characters, you gain fine-grained control over its contents. Modifying strings in Swift involves several methods that let you add, remove, or replace parts of the string. To add characters to the end of a string, use the append method or the += operator. For more precise control, you can insert characters at specific positions using insert at. If you need to remove characters, the remove subrange, remove first, or remove last methods are available. To replace parts of a string, the replace subrange with method allows you to substitute a range of characters with new content. These operations are particularly useful when editing text dynamically, such as in a text editor or a form input handler. Since strings are value types, these modifications create new instances rather than altering the original string. Comparing strings in Swift is essential for tasks like checking user input or validating data. The equality operator == checks if two strings are identical, including their case and Unicode representation. For case-insensitive comparisons, the localized case-insensitive compare method or the hasPrefix case-insensitive and hasSuffix case-insensitive methods methods can be used. These tools help ensure that comparisons are accurate even when dealing with different capitalizations or language-specific rules. Additionally, methods like starts with and ends with provide quick ways to check for specific patterns at the beginning or end of a string. These features make it easier to handle text in a variety of scenarios, from searching for keywords to processing user input. Swift's support for Unicode allows it to handle a vast array of characters, including those from non-English languages, mathematical symbols, and emojis. Strings in Swift are built using Unicode scalar values, which represent individual characters. This approach ensures that text is stored and processed correctly, even for complex scripts that require special formatting or ligatures. For example, a string containing hello, Chinese letter, where Chinese letter is the Chinese word for world, is handled seamlessly. When working with Unicode, it's important to be aware of characters that may consist of multiple scalar values, such as emojis that combine multiple symbols. Swift's Unicode handling makes it possible to create applications that are truly global, supporting users from all over the world. In summary, strings and characters are foundational elements in Swift for working with textual data. Whether you're building a simple app or a complex international application, understanding how to create, manipulate, and compare strings is essential. By leveraging Swift's Unicode support, you can ensure your code works with any language or symbol. Practice using the various methods and properties discussed to become proficient in handling text. As you gain experience, you'll find that strings are not only powerful, but also versatile tools for solving a wide range of programming challenges. Keep exploring and experimenting to deepen your understanding of Swift's text handling capabilities. Optionals are a fundamental concept in the Swift programming language, designed to handle situations where a value might be absent. Unlike other languages where variables can implicitly be nil, Swift requires you to explicitly declare a variable as an optional. This means that a variable can either hold a value of a specific type or be nil, which represents the absence of a value. By using optionals, developers can write safer code because they are forced to consider and handle cases where data might not be available. For example, when retrieving user input or fetching data from a network, there might be instances where the data is missing. And optionals provide a structured way to manage these scenarios without causing runtime errors. To declare an optional in Swift, you add a question mark after the type. For instance, var name string indicates that the variable name can either contain a string value or be nil. Assigning a value to an optional is straightforward, such as name equals Alice or name equals nil, to explicitly set it to an empty state. However, accessing the value of an optional requires a process called unwrapping, which ensures that the value is present before it is used. This step is crucial because directly accessing a nil optional would result in a runtime crash, which is why Swift enforces this safety mechanism. One way to unwrap an optional is by using the exclamation mark, known as forced unwrapping. For example, print name would retrieve the value of name if it is not nil. However, this approach is risky because if the optional is indeed nil, the program will crash at runtime. This can be particularly problematic in production code, where unexpected nil values might occur. While forced unwrapping can be useful in controlled scenarios, it is generally discouraged in favor of safer alternatives. Developers should prioritize methods that handle nil cases gracefully to avoid crashes and ensure a more robust application. A safer method for unwrapping optionals is optional binding, which uses if-let or guard-let constructs. With if-let, you can check if an optional contains a value and then use it within the scope of the if statement. For example, if let safe name equals name, print safe name ensures that safe name is only available if name is not nil. This approach prevents runtime crashes by avoiding direct access to nil values. On the other hand, guard let is used to exit early from a function or method if the optional is nil, allowing for cleaner code structure. By using these techniques, developers can handle nil values in a way that is both safe and readable. The nil coalescing operator, represented by 2 question marks, provides a concise way to handle optional values by specifying a default. For instance, let display name equals name. Guest assigns the value of name to display name if it is not nil. Otherwise, it uses the string guest as a fallback. This operator simplifies code by eliminating the need for multiple conditional checks, making it easier to manage scenarios where a default value is acceptable. By using the nil coalescing operator, developers can write more efficient and readable code while ensuring that their applications handle missing data gracefully. When working with optionals, there are several best practices to keep in mind. First, avoid force unwrapping without proper validation, as it can lead to crashes if the optional is nil. Instead, prefer using optional binding with if let or guard let to safely access values. In complex logic, guard let is particularly useful for early exits, which helps maintain a flat code structure. Additionally, always consider nil as a valid state in your application's design. This means anticipating scenarios where data might be missing and handling them proactively. By following these practices, developers can create more reliable and maintainable Swift code that minimizes the risk of runtime errors. In conclusion, optionals are a critical feature of Swift that enhance code safety by explicitly handling the absence of values. By using constructs like if let, guard let, and the nil coalescing operator, developers can manage optional values effectively while avoiding crashes. It is essential to prioritize safety over convenience, especially when dealing with nil, as this leads to more robust and dependable applications. Mastering optionals is not just about understanding their syntax, but also about adopting a mindset that anticipates and handles missing data gracefully, which is fundamental to becoming a proficient Swift developer. Error handling in Swift is a critical aspect of developing reliable and user-friendly applications. It allows programmers to manage unexpected situations that may occur during the execution of a program. By using the keywords try, catch, and throw, Swift provides a structured way to handle these exceptional conditions. This approach ensures that potential failures are addressed in a controlled manner, which makes the code more robust and predictable. For instance, when a function is expected to perform a task that might fail, such as dividing by 0 or accessing a file that doesn't exist, error handling allows the program to respond gracefully instead of crashing. This not only improves the user experience, but also makes the code easier to debug and maintain. At the core of error handling in Swift is the error protocol, which serves as a marker to indicate that a type can be used as an error. Any custom error type must conform to this protocol, allowing it to be thrown and caught. Functions that can throw errors are declared with the throws keyword, which signals to the caller that the function might not always execute successfully. When a function throws an error, it must be either caught immediately using a try-catch block or propagated further up the call stack. This ensures that errors are not ignored and are handled appropriately, preventing unhandled exceptions that could destabilize the application. By enforcing this structure, Swift promotes a disciplined approach to error management. Throwing functions in Swift are defined with the throws keyword, which indicates that the function may throw an error during its execution. For example, a function named divide that takes two integers and returns an integer can be declared as func divide a int b, int throws int. This syntax makes it clear to developers that the function could potentially fail. When an error occurs, it is thrown using the throw keyword, often accompanied by an instance of an error type. A common example is throwing an NS error object with a specific domain, code, and user info dictionary. This allows for detailed error descriptions, which can be invaluable for debugging and providing meaningful feedback to users. By using throwing functions, developers can separate the normal flow of execution from the error handling logic, making the code cleaner and more modular. The try-catch syntax in Swift is used to handle errors that may be thrown by a function. The basic structure is a do block that contains a try statement, followed by one or more catch blocks to handle specific errors. For example, a do block might attempt to call a throwing function like divide and catch any errors that occur. The catch block can then print an error message, such as the localized description of the error, to inform the user or developer of the issue. This structure allows for multiple catch blocks to handle different types of errors, making the error handling process more precise. By using this syntax, developers can ensure that errors are addressed in a structured and readable way, reducing the likelihood of unhandled exceptions and improving the overall reliability of the code. Error propagation in Swift allows errors to be passed up the call stack, enabling higher-level functions to handle them instead of the immediate caller. This is achieved by declaring functions with the throws keyword, which indicates that they may throw an error. For example, a function named calculate that calls another throwing function like fetch data can propagate the error without handling it itself. This approach is particularly useful in complex applications where multiple layers of functions interact, as it allows errors to be managed at the most appropriate level. By propagating errors, developers can keep the code concise and avoid unnecessary error handling at every level, leading to more maintainable and scalable applications. This mechanism ensures that errors are not silently ignored and are addressed in a context where they can be properly resolved. Creating custom error types in Swift enhances the clarity and specificity of error handling. Instead of using generic error types, developers can define their own error enums that conform to the error protocol. For instance, an enum named network error can include cases like invalid URL, no response, and invalid data to represent different failure scenarios. This approach makes the code more readable and allows for more precise error handling, as each case can be caught and processed individually. Custom errors also provide better context about what went wrong, which is invaluable for debugging and user feedback. By using custom error types, developers can create a more robust and maintainable error handling system that aligns with the specific needs of their application. Mastering error handling in Swift is essential for writing reliable and user-friendly code. The try-catch mechanism allows developers to handle potential failures in a structured and controlled manner, while the throws keyword enables functions to propagate errors up the call stack. Custom error types further improve the clarity and specificity of error messages, making the code easier to understand and maintain. By incorporating these practices into their workflows, developers can create applications that are more resilient to unexpected situations, leading to a better user experience. Whether it's handling division by zero, network issues, or file access problems, effective error handling ensures that the code remains robust and predictable, even in the face of unforeseen challenges. Classes serve as blueprints that define the structure and behavior of objects. When you create a class, you are essentially designing a template that outlines what properties and methods an object of that class will have. Objects, on the other hand, are specific instances of these classes, each with its own unique data. For example, a class called person might define properties like name and age, and methods like greet. These properties and methods are encapsulated within the class, meaning they are grouped together to manage the state and behavior of the object. This encapsulation is a cornerstone of object-oriented programming, which emphasizes organizing code around objects rather than functions and logic. By using classes, developers can create reusable and modular code that models real-world entities more effectively. To declare a class in Swift, you use the class keyword followed by the name of the class. For instance, the code class person var name, string var age. Int defines a class named person with two properties, name and age. The class name should follow the camel case convention, where the first letter is lowercase and subsequent words are capitalized. This naming style helps distinguish classes from other elements in the code. By defining a class, you establish a blueprint that can be used to create multiple objects, each with its own values for the properties. This structure allows for consistency and clarity in managing complex data and functionality. Properties and methods are the two primary components of a class. Properties store the data associated with an object, such as a string for a name or an integer for an age. Methods, on the other hand, define the actions or behaviors that an object can perform. For example, in the dog class, the breed property holds the type of dog, while the bark method outputs a sound. This separation of data and functionality makes code more organized and easier to maintain. By grouping related properties and methods into a single class, you can create objects that behave predictably and interact with other parts of the program in a structured way. Initialization is the process of setting up a class instance with initial values for its properties. In Swift, this is done using the init method, which is called when an object is created. For example, the car class in the code snippet has an init method that takes a make parameter and assigns it to the make property. This ensures that every car object starts with a valid value for its make. If a class has simple properties without default values, Swift can automatically generate a default initializer. However, for more complex setups, explicitly defining an init method gives you full control over how objects are created and configured. To create an object in Swift, you instantiate a class using let or var, followed by the object's name and the class name. For example, let person equals person creates a new instance of the person class. Once the object is created, you can access its properties and methods using the dot notation. In the code snippet, person name Alice assigns a value to the name property, and person.age equals 30 sets the age. This allows you to customize each object's data independently, making it possible to have multiple instances of the same class with different values. Accessing properties and methods in this way is a fundamental aspect of working with objects in Swift. Inheritance is a powerful feature that allows one class to inherit properties and methods from another class. This promotes code reuse and establishes a hierarchical relationship between classes. For example, the vehicle class defines a wheels property, which is then inherited by the bicycle class. The bicycle class can add its own properties, such as has basket, while still retaining the wheels property from the vehicle class. This means that any changes made to the vehicle class automatically apply to all its subclasses, reducing redundancy and making the code easier to manage. Inheritance is a key concept in object-oriented programming, enabling developers to build on existing functionality rather than rewriting it. Overriding methods allows a subclass to provide a new implementation for a method that it inherits from a superclass. This is particularly useful when the subclass needs to modify or extend the behavior of the inherited method. In the example, the animal class has a sound method that prints unknown sound, but the dog class overrides this method to print bark. Instead, the override keyword is essential here, as it explicitly indicates that the method is being redefined. This capability is part of polymorphism, which allows objects of different classes to be treated as objects of a common superclass, enabling flexible and dynamic code behavior. When working with classes in Swift, it's important to follow best practices to ensure clean and maintainable code. For instance, use structs for value types when you need independent copies of data, and classes for reference types when you want multiple instances to share the same data. Encapsulation is key to keeping properties and methods organized and protected from unintended modifications. Avoid deep inheritance hierarchies, as they can become difficult to manage and understand. Instead, consider using composition to combine smaller, focused classes. Finally, use Dainit to perform any necessary cleanup when an object is no longer needed, ensuring efficient memory management. In summary, classes provide a structured way to define objects with specific properties and behaviors, forming the foundation of object-oriented programming. Objects are instances of these classes, each with unique data that can be accessed and modified. Properties and methods work together to organize the state and actions of an object, while inheritance allows for the reuse of code across related classes. Overriding methods and using best practices like encapsulation and composition help create robust and scalable applications. By applying these concepts through real-world examples, you can develop a deeper understanding of how to effectively use classes and objects in Swift. Methods in Swift are functions that are associated with a specific type, such as a class, structure, or enumeration. They allow you to define behavior that can be performed on instances of these types. For example, a method might calculate a value based on the properties of an object or modify those properties. Methods are essential for encapsulating functionality within a type, making code more organized and reusable. The syntax for a method is similar to a function, but includes the type it belongs to. It starts with the keyword func, followed by the method name, parameters, an arrow, and the return type. The body of the method is enclosed in curly braces. This structure enables developers to create clear and concise code that interacts with the data of a type. Instance methods are a type of method that operates on an instance of a type. These methods can access and modify the properties of the instance they belong to, as well as call other methods defined within the same type. For example, an instance method might calculate a value based on the current state of an object. When you create an instance of a class or structure, you can call its methods to perform actions specific to that instance. This is particularly useful for objects that need to maintain and manipulate their own data. Instance methods are fundamental to object-oriented programming in Swift, allowing for dynamic and interactive behavior within your code. Mutating methods are used to modify the properties of value types, such as structures and enumerations. Unlike instance methods, which can only read properties by default, mutating methods explicitly allow changes to the properties of a value type. This is necessary because value types are copied when they are assigned or passed around, so any modifications must be done in place. To declare a mutating method, you use the mutating keyword before the func keyword. For example, a mutating method might toggle a Boolean property or update a numeric value. This ensures that the changes are applied directly to the instance without creating a new copy, which is crucial for maintaining the integrity of value types. The key difference between regular methods and mutating methods lies in their ability to modify properties of value types. Regular methods cannot alter the properties of a value type because they are designed to work with immutable data. In contrast, mutating methods explicitly allow modifications to the properties of a structure or enumeration. This distinction is important because it enforces immutability by default, which is a core principle in Swift. However, when you need to change the state of a value type, you must use the mutating keyword. This feature is not applicable to classes because they are reference types and can be modified directly without the need for an explicit keyword. Understanding this difference helps developers write safer and more predictable code. Let me provide some examples to illustrate these concepts. An instance method might be used to describe an object, such as printing a message based on its properties. For example, a method called describe could output a string that includes the type of the instance. A mutating method, on the other hand, might be used to toggle a Boolean property, like changing the active state of an object. In this case, the method uses the mutating keyword to indicate that it will modify the instance. When comparing classes and structures, it's important to note that classes can modify their properties without the mutating keyword because they are reference types. Structures, however, require the mutating keyword to allow in-place changes to their properties. This distinction highlights the differences between value and reference types in Swift. In summary, methods are a fundamental part of Swift programming, allowing you to define behavior for types and interact with their properties. Mutating methods play a crucial role in modifying value types, such as structures and enumerations, ensuring that changes are made in place. By using the mutating keyword, you can explicitly allow modifications to value types, which helps maintain immutability by default. Understanding when to use instance methods versus mutating methods is essential for writing efficient and readable code. Whether you are working with classes, structures, or enumerations, these concepts will guide you in creating robust and maintainable Swift applications. Inheritance is a fundamental concept in object-oriented programming that allows one class to inherit properties and methods from another class. This mechanism promotes code reusability by enabling you to define a base class with common functionality, and then build upon it with more specific classes. The class that provides the shared functionality is called a superclass, while the class that inherits from it is referred to as a subclass. This hierarchical structure not only makes your code more organized, but also simplifies maintenance and updates. For example, if you have a class that represents a vehicle, you can create subclasses like car or bicycle that inherit the vehicle's properties and methods while adding their own unique features. A superclass serves as a base class that contains shared functionality, while a subclass is a derived class that extends or modifies this functionality. For instance, consider a superclass called vehicle, which might have properties like wheels and methods like start engine. A subclass like car would inherit all these members, allowing it to use the wheels property and the start engine method without redefining them. However, the subclass can also add new properties, such as brand, or override existing methods to provide a more specific implementation. This relationship allows for a clear and logical organization of code, making it easier to manage complex systems by breaking them down into smaller, more manageable components. To define a superclass in Swift, you use the class keyword followed by the class name. A superclass can include properties, methods, and initializers that other classes can inherit. For example, the vehicle class might have a property called wheels that stores the number of wheels, and a method called start engine that prints a message. These elements are accessible to any subclass that inherits from vehicle. Superclasses act as a foundation for other classes, allowing them to build upon existing functionality. This approach reduces redundancy and ensures that common behaviors are defined in a single place, making the code base more consistent and easier to maintain. Creating a subclass in Swift involves using the class keyword followed by the subclass name and a colon, then specifying the superclass. For example, the car class could be defined as a subclass of vehicle, inheriting all its properties and methods. This means that a car instance would automatically have access to the wheels property and the start engine method from the vehicle class. Subclasses can also introduce new properties and methods to extend the functionality of the superclass. This ability to build upon existing classes is a powerful feature of object-oriented programming, enabling enabling developers to create flexible and scalable applications. The super keyword in Swift is used to refer to the superclass instance. It allows you to call methods or access properties defined in the superclass. For example, if a subclass overrides the start engine method, it can still call the superclass's version of the method using super start engine. Similarly, you can access the superclass's properties with superwheels. This is particularly useful in initializers, where the subclass must call the superclass's initializer to ensure proper initialization. By using super, you maintain a clear connection to the superclass's implementation, while allowing the subclass to add or modify behavior as needed. Overriding methods in a subclass allows you to provide a new implementation for a method that was defined in the superclass. This is done using the override keyword, which tells Swift that you intend to replace the superclass's method. For example, if the vehicle class has a start engine method, the car subclass can override it to print a message specific to a car. This feature is essential for customizing inherited behavior to suit the needs of the subclass. Overriding enables you to create more specific and tailored implementations while still benefiting from the shared functionality of the superclass. It's a key aspect of polymorphism, allowing different classes to respond to the same method call in their own way. When initializing a subclass in Swift, it is mandatory to call one of the superclass's initializers. This ensures that the superclass's properties are properly initialized before the subclass adds its own. For example, a car subclass might have an initializer that sets the brand property and then calls Serenade to invoke the vehicle class's initializer. This order is crucial because the subclass's properties depend on the superclass being fully initialized first. By adhering to this rule, you avoid potential errors and ensure that all parts of the object are correctly set up. This practice is a cornerstone of safe and reliable object-oriented programming. Inheritance offers several key benefits that make it a vital tool in software development. First, it allows for code reuse, reducing duplication and making your code base more efficient. By defining common functionality in a superclass, you can avoid rewriting the same code in multiple classes. Second, inheritance creates hierarchical relationships, making it easier to organize and understand complex systems. Third, It simplifies maintenance and updates, as changes to the superclass automatically propagate to all subclasses. Finally, inheritance enables polymorphism, allowing objects of different classes to be treated as instances of a common superclass. This flexibility is essential for building dynamic and scalable applications. Inheritance is a core concept in Swift's object-oriented programming model, allowing classes to share and extend functionality. Superclasses provide a foundation of shared properties and methods, while subclasses build upon this foundation to create more specific implementations. The super keyword plays a critical role in accessing and calling the superclass's members, ensuring a seamless integration between classes. By mastering inheritance, you can create organized, reusable, and maintainable code. As you practice, try building class hierarchies for real-world scenarios, such as modeling different types of vehicles, animals, or user interfaces. This hands-on experience will deepen your understanding and help you apply inheritance effectively in your projects. Protocols in Swift serve as blueprints that define a set of methods, properties, and other requirements that a type can adopt. They act as a contract, ensuring that any type conforming to a protocol adheres to a specific interface. This abstraction allows different types, such as classes, structures, and enumerations, to share a common set of behaviors without being tied to a specific inheritance hierarchy. By using protocols, developers can decouple code, making it more modular and easier to maintain. For example, a protocol named vehicle could require a method called start-engine, which any type conforming to vehicle must implement. This approach fosters flexibility and reusability in code design. The syntax for declaring a protocol in Swift begins with the keyword protocol, followed by the protocol name. Inside the protocol, you define the requirements that conforming types must satisfy. These requirements can include methods, properties, and even initializers. For instance, a protocol called drawable might require a method named draw, and a property called color that has a getter. This structure ensures that any type adopting drawable must provide its own implementation of these requirements. The example given demonstrates how a protocol can encapsulate a set of behaviors that multiple types can share, while allowing each type to define its own unique characteristics. When a type adopts a protocol, it must implement all the requirements defined by that protocol. This is done by appending a colon and the protocol name to the type declaration. For example, a structure named circle can adopt the drawable protocol by implementing the required methods and properties. In the example provided, the circle structure implements the draw method and provides a value for the color property. This process ensures that the type adheres to the protocol's interface, allowing it to be used interchangeably with other types that conform to the same protocol. By enforcing this structure, protocols enable consistent and predictable behavior across different parts of an application. Protocol extensions allow developers to add default implementations to protocols, reducing the need for repetitive code in conforming types. This feature is particularly useful when multiple types share common functionality. For example, an extension on the drawable protocol can provide a default implementation of the draw method, which any type conforming to drawable can use unless it overrides the method. This approach simplifies the development process by allowing developers to define shared behavior once and reuse it across multiple types. Protocol extensions also make it easier to add new functionality to existing protocols without modifying the conforming types. Default implementations in protocols provide a fallback behavior that conforming types can use if they do not override the method. This is especially valuable when the default behavior is suitable for most use cases, but some types may need to customize it. For instance, a square structure that adopts the drawable protocol might not need to implement the draw method if the protocol extension already provides a default implementation. This flexibility allows developers to write more concise code while still maintaining the ability to tailor behavior for specific types. By leveraging default implementations, developers can reduce boilerplate code and focus on the unique aspects of each type. Conditional extensions enable developers to extend protocols with specific constraints, allowing for more targeted functionality. This is achieved using the where clause to specify type requirements. For example, an extension on the sequence protocol can be limited to types where the element conforms to equatable. Adding a contains method that checks for the presence of an element. This approach ensures that the extension is only applied to types that meet the specified conditions, avoiding unnecessary complexity. Conditional extensions are a powerful tool for adding specialized behavior to subsets of types, making code more efficient and easier to manage. Protocol-oriented programming shifts the focus from traditional inheritance hierarchies to defining interfaces through protocols. This approach encourages the creation of reusable and flexible code by emphasizing shared behaviors rather than rigid class structures. For example, dependency injection can be implemented using protocols, allowing different implementations to be swapped in and out without affecting the dependent code. By prioritizing interfaces, developers can design systems that are easier to test, maintain, and extend. This paradigm promotes a more modular and scalable architecture, making it a cornerstone of modern Swift development. The benefits of protocol extensions are numerous, as they allow functionality to be shared across multiple types without the need for subclassing. This is akin to a mix-in pattern, where a type can adopt additional behaviors without being tied to a specific class hierarchy. Protocol extensions also simplify code maintenance by centralizing common implementations, making it easier to update and test shared logic. Additionally, they reduce the complexity of large code bases by enabling developers to add new features to existing protocols without modifying the conforming types. This approach fosters a more cohesive and maintainable code base, ultimately improving developer productivity. Protocol extensions are commonly used to add default methods to protocols, such as equatable and comparable, which are fundamental to Swift's standard library. These extensions provide a baseline implementation that can be customized by conforming types, ensuring consistency across the code base. Another use case involves adding utility functions that enhance the capabilities of conforming types without requiring changes to their original definitions. Protocol extensions also play a role in bridging Swift with Objective-C, allowing developers to add methods that can be accessed from Objective-C code. These practical applications highlight the versatility and power of protocol extensions in real-world development scenarios. In conclusion, protocols and extensions are essential tools for building modular, reusable, and maintainable Swift code. By By defining interfaces and sharing functionality across types, developers can create more flexible and scalable applications. Mastering these concepts is crucial for advanced Swift development, as they enable the creation of robust and efficient systems. To fully leverage protocols and extensions, it is important to practice by designing custom protocols and extending existing ones. This hands-on approach will deepen your understanding and help you apply these powerful features in your own projects. Structs and classes are foundational building blocks in the Swift programming language, designed to help developers organize and structure their code effectively. Both allow you to define properties and methods, which are the characteristics and behaviors of a type. However, their underlying mechanics and use cases diverge significantly. Understanding these differences is crucial for writing code that is not only efficient, but also easy to maintain and scale. For instance, choosing the right type can prevent unintended side effects, optimize performance, and ensure clarity in how data is managed. This presentation will explore these distinctions in depth, helping you make informed decisions when designing your Swift applications. In Swift, structs are value types, meaning that whenever you assign a struct to a new variable or pass it to a function, a copy of the entire value is created. This ensures that changes to one instance do not affect others, promoting data integrity. On the other hand, classes are reference types, which means that when you assign or pass a class instance, you are working with a reference to the same underlying object. This allows multiple variables to point to the same instance, enabling shared state and dynamic behavior. The choice between value and reference types has profound implications for how data is handled, particularly in scenarios involving concurrency or large data sets. Value types are inherently safer for multi-threaded environments, while reference types offer flexibility for shared modifications. One of the most significant differences between structs and classes lies in their support for inheritance and polymorphism. Classes in Swift can inherit properties and methods from other classes, allowing for hierarchical relationships and code reuse. This is the cornerstone of object-oriented programming, enabling you to create a base class with common functionality and extend it with specialized subclasses. For example, a vehicle class could be inherited by car and bike subclasses, each adding unique behaviors. Structs, however, cannot inherit from other types, nor can they be subclassed. This limitation makes structs ideal for data-centric designs, where composition and encapsulation are more important than hierarchical relationships. If your goal is to build a system with shared behavior across multiple types, classes are the right choice. Mutability and immutability are key considerations when choosing between structs and classes. By default, structs are immutable, meaning that once created, their properties cannot be modified unless explicitly declared with the var keyword. This default immutability encourages safer code, as it prevents unintended changes to data, especially in complex or concurrent environments. Classes, by contrast, are mutable by default, allowing their properties to be modified after initialization. This flexibility is useful when you need to track changing state, such as a user's profile information or a game's dynamic elements. However, the mutability of classes also requires careful management to avoid side effects. When designing your types, consider whether immutability aligns with your use case, as it can simplify debugging and improve thread safety. Memory management in Swift is another critical factor that differentiates structs and classes. Structs are allocated on the stack, which is a faster and more efficient memory region, and they are deallocated automatically when they go out of scope. This makes them ideal for small, temporary data structures. Classes, however, are allocated on the heap, a more flexible but slower memory region, and their memory is managed by automatic reference counting arc. Arc ensures that instances are deallocated when they are no longer needed, preventing memory leaks. While structs avoid the overhead of manual memory management, their stack allocation can lead to copy overhead when they are passed around frequently. Classes, though more flexible, require careful handling to avoid retained cycles and ensure optimal performance. Understanding these trade-offs can help you choose the right type for your specific needs. Deciding when to use structs versus classes depends on the nature of the data and the requirements of your application. Structs are best suited for small, self-contained data structures that do not require inheritance or shared state. Examples include geometric shapes like points and rectangles, or data models such as a user's name and email. Their value semantics ensure that copies are isolated, making them predictable and safe to use in complex workflows. Classes, on the other hand, are ideal for modeling complex objects that need to maintain state across multiple interactions or share data with other parts of the system. They are also the go-to choice when you need to leverage inheritance and polymorphism for code reuse. In performance-critical scenarios, structs often outperform classes due to their stack allocation and reduced overhead. However, for object-oriented designs where shared behavior and dynamic interactions are essential, classes provide the necessary flexibility. In summary, structs and classes in Swift serve distinct purposes and are chosen based on the specific requirements of your project. Structs offer value semantics, immutability by default, and efficient memory allocation, making them ideal for data-centric designs. Classes provide reference semantics, mutability, and support for inheritance, making them suitable for complex, object-oriented systems. By understanding these differences, you can write code that is not only efficient, but also more maintainable and scalable. Whether you are building a simple data model or a large-scale application, the choice between structs and classes will shape the behavior and performance of your code. Always consider the trade-offs between immutability, shared state, and inheritance to make the best decision for your use case. Access control is a fundamental concept in Swift that helps manage the visibility of code elements such as classes, functions, variables, and other declarations. By restricting access, we ensure that parts of our code are only available where they need to be, which promotes encapsulation and reduces the risk of unintended dependencies. This makes our code more modular, easier to maintain, and less prone to errors. Swift provides specific modifiers to define access levels, which determine how and where these elements can be accessed. These modifiers include public, internal, private, and file private. Understanding how to use them effectively is crucial for writing clean and secure Swift code. Swift offers 4 primary access levels to control the visibility of code elements. The public access level allows elements to be accessed from any source file within the same module, or even from other modules that import the code. This is ideal for APIs or components that need to be used across different parts of a project or by external frameworks. The internal access level is the default in Swift, meaning that elements are accessible only within the same module. This is perfect for code that is part of the same project, but doesn't need to be exposed outside. The private access level restricts access to the immediate enclosing scope, such as a class or function, ensuring that sensitive data or implementation details remain hidden. Lastly, the file private access level allows access within the same source file, making it useful for helper functions or variables that are shared across a file, but not needed outside of it. Each level serves a specific purpose and should be chosen based on the desired scope of accessibility. The public access modifier is used to expose elements to other modules, making them available for use in external code. For example, if you define a class as public, it can be instantiated and used in any other file or module that imports the code. Similarly, public functions or methods can be called from outside the module. This is essential for creating APIs or frameworks that other developers can integrate into their projects. However, it's important to use public modifiers judiciously. Overusing them can lead to tight coupling between modules, making the code harder to maintain or update. By limiting public access to only what is necessary, we can ensure that our code remains flexible and robust. Internal access is the default level in Swift, meaning that any code not explicitly marked with a modifier is considered internal. This makes it accessible within the same module, such as different files in the same project or framework. For example, if you define a class without any access modifier, it is automatically internal, and its members can be accessed by other parts of the same module. Internal access is ideal for code that is part of the internal implementation and does not need to be exposed outside the module. This helps keep the code base organized by separating public interfaces from private or internal details. By relying on internal access for most of the code, we can maintain a clear boundary between what is intended for external use and what is meant for internal operations. The private access modifier is used to restrict access to the immediate enclosing scope, such as a class, struct, or function. For instance, if a variable is marked as private within a class, it can only be accessed by other members of that class. This is particularly useful for protecting sensitive data or implementation details that should not be modified or accessed from outside the class. Private access ensures that the internal state of an object remains encapsulated, reducing the risk of unintended side effects. However, it's important to note that private modifiers cannot be applied to top-level functions or types. Instead, they are reserved for nested declarations, allowing developers to control access at a granular level. This level of control is essential for maintaining the integrity of an object's internal state. The file private access modifier is used to limit access to the same source file, making it ideal for code that is shared across multiple functions or types within a single file. For example, a helper function that is used by several methods in the same file can be marked as file private to ensure it is not accessible outside of that file. This helps keep implementation details hidden while still allowing them to be reused within the file. File private access is particularly useful for organizing code in larger files, where certain functions or variables are not meant to be part of the public interface. By using file private, developers can avoid exposing internal logic to other files, which enhances code security and maintainability. When working with classes, access control determines how members of the class can be accessed from outside the class or other modules. Private members are only visible within the class itself, ensuring that they cannot be modified or accessed by external code. File private members are accessible within the same source file, allowing them to be used by other types or functions in that file. Internal members are accessible throughout the entire module, making them suitable for code that is part of the module's internal logic. Finally, public members are available across all modules, making them ideal for APIs or components that need to be used externally. Choosing the right access level for class members is critical for balancing flexibility and security, ensuring that the class's internal state remains protected while exposing only what is necessary. Extensions in Swift inherit the access level of the original declaration they are extending. For example, if a class is marked as private, any extensions of that class will also be private by default. This ensures consistency and prevents unintended access to members that are not meant to be modified. However, if an extension needs to access or modify members with a higher access level, it must explicitly use a modifier such as file private or public. This allows developers to control how extensions interact with the original type, ensuring that changes are made in a safe and predictable way. It's important to maintain consistency between the original type its extensions, as mismatched access levels can lead to errors or unexpected behavior. By carefully managing access levels in extensions, developers can maintain a clean and organized code base. Adhering to best practices for access control is essential for writing clean, maintainable, and secure Swift code. One key principle is to use the least restrictive access level necessary. This means avoiding public modifiers for code that doesn't need to be accessed externally, as it reduces the risk of unintended dependencies. By default, developers should mark types and members as private or file private, limiting their visibility to only what is required. This approach helps protect internal implementation details and prevents external code from modifying them. For code that is used within the same module, internal access is often the best choice, as it provides a clear boundary between internal and external components. By following these guidelines, developers can create more modular and robust applications. Access control is a powerful feature in Swift that enhances code safety, maintainability, and modularity. By understanding and applying the different access levels, public, internal, private, and file private, developers can control how their code is used and accessed. This not only helps prevent errors, but also makes it easier to manage and update code over time. Strategic use of access control ensures that only the necessary parts of a code base are exposed, promoting encapsulation and reducing coupling between modules. Following Swift's conventions for access control allows developers to create secure and scalable applications. Whether building small utilities or large frameworks, mastering access control is an essential skill for any Swift developer. Generics are a powerful feature in Swift that allow functions and types to operate on any data type. This means you can write code that is not tied to a specific type, making it more versatile and adaptable. By using generics, you can avoid writing repetitive code for different types, which significantly improves code reusability. Additionally, generics enhance type safety by ensuring that the data you work with is always of the correct type. For example, Swift's standard library uses generics extensively in structures like arrays and dictionaries. These collections can hold elements of any type, whether it's integers, strings, or custom objects, while still maintaining strict type checking. This flexibility makes generics an essential tool for building robust and scalable applications. Type parameters are placeholders that represent specific types in generic code. They are defined using angle brackets, such as T or U, where T and U are arbitrary names chosen by the developer. For instance, a function like swap_t allows you to swap the values of two variables regardless of their type. This approach eliminates the need to write separate functions for each data type, such as a swap function for integers and another for strings. By using type parameters, you can create functions that are both flexible and concise, adapting to any type that is passed into them. This not only reduces code duplication, but also makes your code easier to maintain and extend. Generic functions take this concept further by allowing functions to accept type parameters as arguments. For example, a function like findMaxT comparable can compare any two values as long as the type conforms to the comparable protocol. This means the function works seamlessly with integers, strings, or even custom types that implement the required functionality. By leveraging protocols like comparable, you can write functions that are both reusable and type-safe. This approach reduces the need for multiple function overloads, where you would otherwise have to write separate functions for each type. Generic functions are a cornerstone of Swift's design, enabling developers to create efficient and adaptable code. Generic types extend the concept of generics to custom data structures. For example, a stack T can hold elements of any type, such as numbers, characters, or even complex objects. This flexibility means you can create a single stack implementation that works with ints, strings, or any other type you choose. The key advantage of generic types is that they maintain type safety, ensuring that you cannot accidentally add an element of the wrong type to the stack. This makes your code both more reliable and easier to use. By defining types with generics, you can build reusable components that are as flexible as they are safe, which is especially valuable in large-scale applications. Constraints in generics allow you to limit the types that can be used with a generic function or type. For example, a function like print value t, custom string convertible ensures that only types conforming to the custom string convertible protocol can be passed to it. This guarantees that the function can access the required methods or properties of the type. Constraints can also be combined, using where clauses to enforce more complex conditions. For instance, you might require a type to conform to multiple protocols or to be a subclass of a specific class. These constraints ensure that your generic code is used correctly, preventing runtime errors and making your code more predictable and maintainable. Associated types allow protocols to define placeholder types that are determined by the conforming type. For example, a container protocol might have an associate type item, which represents the type of elements the container holds. This enables the protocol to work with different types dynamically, such as an array of integers or a dictionary of strings. Associated types are widely used in Swift's standard library, including in types like dictionary and array, where they allow the compiler to infer the correct types automatically. This feature makes protocols more flexible and powerful, enabling them to work with a wide range of data types while maintaining type safety and clarity. Extensions with generics allow you to add new functionality to existing types without modifying their original implementation. For example, an extension on array where element equatable can add methods that compare arrays for equality. This approach keeps your code modular and reusable, as you can apply the same logic to different types that meet the required constraints. Extensions with generics are particularly useful for adding utility functions to standard library types, such as checking if an array contains a specific element or sorting its contents. By leveraging generics in extensions, you can create code that is both flexible and easy to maintain, enhancing the capabilities of existing types without altering their original definitions. Swift's standard library includes several built-in generic types that are fundamental to the language. For example, optional T is used to represent values that may be absent, allowing you to handle missing data safely. Arrays and dictionaries are also generic, with array T and dictionary key, value-enabling collections of any type. Another example is result T error, which encapsulates the outcome of an operation, whether it succeeds with a value of type T or fails with an error. These generic types form the backbone of Swift's type system, providing the flexibility and safety needed to build complex applications. Understanding how to use and extend these built-in generics is essential for mastering Swift's capabilities. When working with generics, it's important to follow best practices to ensure your code remains clean and maintainable. First, use generics to avoid duplicating code across different types, which reduces the risk of errors and simplifies updates. Instead of relying on force casting or type checking, prefer constraints to ensure compatibility between types. Keep type parameters focused and simple, as overly complex generics can make your code harder to understand. Finally, document your generic code thoroughly, explaining the purpose of type parameters and any constraints. These practices help create code that is not only functional, but also easy for others to read and extend, which is crucial for collaborative development. In summary, generics are a critical feature of Swift that enable you to write reusable, type-safe code. By mastering type parameters and constraints, you can create functions, types, and protocols that work with a wide range of data types without sacrificing safety or clarity. Applying generics to your code allows you to build more efficient and scalable applications, reducing redundancy and improving maintainability. As you continue to explore Swift, practice implementing generics in real-world scenarios, such as creating custom data structures or extending existing types. This hands-on experience will solidify your understanding and help you leverage generics to their full potential. Enums in Swift are a powerful way to define a common type for a group of related values. They allow you to create a single, cohesive type that can represent multiple possibilities, making your code more organized and expressive. For example, an enum called day can encapsulate the days of the week as distinct cases. This approach ensures that you work with a fixed set of values, reducing errors and improving clarity. By using enums, you can model real-world scenarios where a variable must take on one of several predefined options, such as the status of a task or the type of a user action. This not only enhances type safety, but also makes your code more readable and maintainable. Associated values take enums to the next level by allowing you to attach additional information to each case. This means that each enum case can carry its own unique data, making the enum more versatile. For instance, a shape enum can have a circle case with a radius and a square case with a side length. This capability is particularly useful when you need to represent data that varies in structure but belongs to the same type. By using associated values, you can store different types of data within a single enum, enabling more dynamic and flexible code. This feature is especially valuable in scenarios where the same action or state might require different parameters or data types. The syntax for associated values in Swift is straightforward and intuitive. When defining an enum case with associated values, you use parentheses to specify the types and names of the values. For example, the result enum can have a success case that holds a string and a failure case that holds an integer. This structure allows you to clearly define what data each case can carry. The general syntax is case, name, value type. Value type, which makes it easy to see what information is associated with each case. This approach ensures that the data is tightly coupled with the enum case, maintaining type safety and making the code more self-explanatory. Let's look at a practical example of how associated values can be used in real-world scenarios. Consider a network response enum that represents the outcome of a network request. The success case can store data, such as a JSON payload, while the error case can hold an error code and a message. This design allows you to handle different types of responses within a single, unified type. By associating specific data with each case, you can easily access and process the information when needed. This approach is particularly useful in applications that interact with APIs, where responses can vary significantly in structure and content. To work with associated values effectively, you use switch statements to match and extract the data. When you switch on an enum value, you can destructure the associated values and use them in your code. For example, if a response is a success, you can extract the data and display it. If it's an error, you can retrieve the code and message to handle the issue. This pattern ensures that you handle all possible cases explicitly, reducing the risk of runtime errors. The switch statement acts as a powerful tool for pattern matching, allowing you to access and utilize the associated values in a safe and structured way. Enums can also have multiple associated values within a single case, enabling complex data structures. For instance, a user action enum might have a login case that requires both a username and a password. This allows you to model scenarios where an action involves multiple parameters. By grouping related data into a single case, you can maintain clarity and avoid cluttering your code with separate variables. This capability is particularly useful in applications that require handling intricate user interactions or state transitions, where each action might need to carry several pieces of information. You should use associated values whenever you need to store additional data with specific enum cases. This is especially useful when dealing with heterogeneous data, where different cases might require different types of information. For example, when parsing JSON data, you might have cases that represent different types of objects, each with its own set of properties. Associated values allow you to handle these variations in a type-safe manner. They are also helpful in modeling game states, where each state might have unique parameters, or in error handling, where different errors might carry different details. This feature makes enums a flexible tool for a wide range of programming challenges. When working with enums and associated values, it's important to follow best practices to keep your code clean and maintainable. One key principle is to keep data and behavior together, ensuring that each case is responsible for its own associated values. Avoid overloading enums with too many cases or values, as this can make the code difficult to manage. Instead, prioritize clarity and simplicity by designing enums that are easy to understand and extend. By focusing on these principles, you can create enums that are both powerful and intuitive, enhancing the overall quality of your Swift code. Enums with associated values are a cornerstone of Swift's type system, offering both flexibility and type safety. They allow you to encapsulate complex data within a single, unified type, making your code more expressive and robust. By mastering this concept, you can write more maintainable and scalable applications, capable of handling a wide range of scenarios. Whether you're building a simple app or a complex system, enums with associated values provide a powerful way to model your data and interactions. Embracing this feature will help you write cleaner, more efficient Swift code that is both expressive and easy to work with. Extensions are a powerful feature in Swift that allow developers to add new functionality to existing types without modifying their original definitions. This means you can enhance classes, structs, enums, and protocols with new methods, computed properties, initializers, and subscripts. By using extensions, you can expand the capabilities of a type without subclassing, which helps maintain clean and modular code. For example, you might add a method to a string type to format it in a specific way, or introduce a computed property to an integer type that calculates a value based on its current state. This approach keeps the original type unchanged while making it more versatile for different use cases. The syntax for creating an extension is straightforward. You start with the keyword extension, followed by the name of the type you want to extend. For instance, to add a greet method to the string type, you would write an extension block with the method inside. This example demonstrates how to create a function that prints a greeting using the self parameter, which refers to the instance of the type. Extensions can be defined in the same file as the original type or in separate files, which is particularly useful for organizing large code bases. By keeping extensions in separate files, you can manage the code more efficiently and avoid cluttering the original type's definition. Extensions are not limited to adding methods. They can also introduce computed properties, subscripts, and initializers. For example, you can add a computed property to the int type that checks if a number is even by using the modulo operator. This property would return a Boolean value based on the current instance's value. Similarly, you can define an instance method that calculates the square of an integer. These additions become available to all instances of the type, making the functionality reusable across the entire code base. This approach is especially valuable when you want to add utility functions or properties that are relevant to all instances of a type, such as formatting numbers or performing common calculations. Protocols in Swift define a blueprint of methods, properties, and other requirements that a type must implement. When a type adopts a protocol, it fulfills these requirements to use the protocol's functionality. However, sometimes a type might not have the necessary methods or properties to conform to a protocol. This is where extensions come into play. By using an extension, you can add the required functionality to an existing type, allowing it to adopt a protocol without modifying its original definition. This is particularly useful when working with third-party types, or when you cannot change the original code. Extensions provide a flexible way to adapt existing types to new interfaces, enhancing their interoperability with other parts of the code. One of the most common uses of extensions is to make existing types conform to protocols. For example, if you have a protocol called printable that requires a description method, you can use an extension to add this method to the string type. This allows the string type to fulfill the protocol's requirements without altering its original implementation. By doing so, any instance of string can now use the description method as defined in the extension. This technique is especially useful for adding functionality to types that are not under your control, such as types from external libraries or frameworks. It also helps keep the codebase organized by separating protocol conformance logic from the type's original definition. Swift 5.9 introduced new attributes that make it easier to provide default implementations for protocol methods. The @default attribute allows a protocol method to have a default implementation, which can be overridden by the adopting type if needed. For example, a loggable protocol might have a log method with a default implementation that prints a standard message. This means that any type conforming to loggable can use this default behavior without needing to implement the method themselves. Extensions can be used to provide these default implementations, reducing the boilerplate code required for protocol conformance. This feature enhances flexibility as it allows developers to define protocols with optional behaviors while maintaining backward compatibility. In summary, extensions are a fundamental tool in Swift for enhancing existing types and improving code organization. They allow you to add functionality without modifying the original type, making your code more modular and easier to maintain. By using extensions to adopt protocols, you can make types conform to interfaces without altering their original definitions, which is especially useful for third-party types. Extensions also enable the addition of default implementations for protocols, reducing the need for repetitive code. Overall, extensions are a versatile and efficient way to expand the capabilities of your types, leading to cleaner and more reusable code. By leveraging extensions effectively, you can write more expressive and maintainable Swift programs. Memory management is the process of allocating and deallocating memory for objects in an application. This ensures that your app uses resources efficiently and doesn't consume more memory than necessary. When an app runs, it creates objects that require memory, and managing this properly is crucial for performance. If memory is not released when it's no longer needed, it can lead to memory leaks, which can cause the app to slow down or even crash. Swift addresses this challenge through a feature called automatic reference counting, which automates the management of memory for you. This means developers don't have to manually track and release objects, reducing the risk of errors and making the development process more efficient. ARC stands for Automatic Reference Counting. It is a compiler feature that automatically manages memory by tracking and releasing objects when they are no longer needed. This eliminates the need for manual memory management, which used to involve writing code like retain, release, or auto-release. With ARC, the compiler inserts these calls for you, making memory management much simpler. ARC works with classes, closures, and other reference types, ensuring that objects are deallocated as soon as they are no longer in use. This automation not only saves time, but also helps prevent common memory-related bugs that can be difficult to track down. ARC operates by maintaining a reference count for each object. Every time an object is referenced, the count increases, and when a reference is removed, the count decreases. This process is entirely handled by the compiler, so developers don't have to worry about manually managing these increments and decrements. When the reference count reaches 0, it means no part of the app is using the object anymore, and the system automatically deallocates it. This ensures that memory is freed up as soon as possible, improving the app's performance. ARC also handles the retain, release, and auto-release operations seamlessly, so developers can focus on building features rather than managing memory. A retain cycle occurs when 2 or more objects strongly reference each other, creating a loop that prevents them from being deallocated. This is a common issue in scenarios where objects hold strong references to each other, such as in delegate patterns or closures that capture self. When a retain cycle forms, the reference counts of the objects involved never reach 0, so the memory they occupy is never freed. This leads to memory leaks, which can cause the app to use more memory than necessary and potentially crash. Retain cycles are particularly tricky because they can be hard to detect and may only become apparent under specific conditions. To break retain cycles, developers should use weak or unowned references instead of strong references in situations where objects might reference each other. Weak references are optional and automatically set to nil when the referenced object is deallocated, making them safe to use in cases where the relationship is not guaranteed. Unowned references, on the other hand, are non-optional and assume the referenced object will always exist for the duration of the reference. By replacing strong references with these alternatives, developers can prevent retained cycles and ensure that memory is properly released when objects are no longer needed. Weak and unowned references serve different purposes and should be used based on the relationship between objects. Weak references are ideal for optional relationships where the referenced object might be deallocated at any time. For example, a delegate often uses a weak reference because the delegate could be deallocated before the object that holds it. Unowned references are better suited for non-optional relationships where the referenced object is guaranteed to exist for the entire lifetime of the reference. An example is a parent-child relationship where the child is always owned by the parent. Using the correct type of reference ensures that memory is managed safely and efficiently. Following best practices for memory management is essential to avoid common pitfalls. One key practice is to always use weak or unowned references for delegate and closure references, as these are common sources of retained cycles. When writing closures, developers should also be cautious about capturing self strongly, as this can create unintended retained cycles. Instead, using a capture list to mark closures as weak or unowned helps prevent this issue. Additionally, implementing the DANIT method allows developers to clean up any resources that need explicit release, ensuring that objects are properly disposed of when they are no longer needed. These practices contribute to a more stable and efficient app. Common pitfalls in memory management often stem from oversight or misunderstanding of reference types. One frequent mistake is forgetting to mark closures as weak or unowned in capture lists, which can lead to retained cycles. Developers should always check their closures to ensure they do not hold strong references to self or other objects. Another issue is creating strong reference loops in delegate patterns or closures, which can be difficult to detect. Overusing unowned references when the referenced object might be deallocated is another risk, as it can lead to crashes if the object is no longer available. By being mindful of these issues and testing thoroughly, developers can avoid memory leaks and ensure their apps run smoothly. Arc simplifies memory management in Swift, but requires awareness of potential issues like retained cycles. While the compiler handles most of the work, developers must still make informed decisions about reference types to ensure memory is managed correctly. Using weak and unowned references appropriately is crucial for breaking strong reference loops and preventing memory leaks. By following best practices, such as marking closures and delegates as weak or unowned, and implementing DANIT methods when necessary, developers can maintain efficient app performance. Understanding these concepts allows for more robust and reliable code, ensuring that apps run smoothly and use resources effectively. Optionals in Swift are a powerful feature that allows variables to represent values that can be either present or absent. This means an optional can hold a value of a specific type or be set to nil, which signifies the absence of a value. They are particularly useful when dealing with situations where a value might not be available, such as when retrieving data from an external source, or when a variable hasn't been initialized yet. By using optionals, Swift ensures that developers handle the possibility of nil values explicitly, which helps prevent runtime crashes that can occur when trying to access a value that doesn't exist. For example, if you have a variable that might not have a value, declaring it as an optional allows you to safely check for its presence before using it. This makes optionals a core concept in Swift programming, as they encourage safer and more predictable code. To declare an optional variable in Swift, you add a question mark after the type. For instance, if you want a variable to hold a string value, but it might not have one, you would write var username, string question mark. This tells Swift that username can either contain a string or be nil. Assigning a value to an optional is straightforward, like username equals John. However, if you try to access the value without checking if it exists, you might encounter an error. That's why it's important to unwrap the optional before using its value. This can be done using optional binding or forced unwrapping, but each method has its own use cases and risks. Understanding how to declare and manage optionals is essential for writing robust Swift code. Forced unwrapping is a technique used to access the value of an optional when you are certain it contains a value. This is done by adding an exclamation mark to the end of the optional variable, such as username. In the example, while this approach can be useful in situations where you are confident the optional has a value, it comes with significant risks. If the optional is actually nil, your app will crash, which can lead to a poor user experience. For example, if you try to access username, when username has been set to nil, the program will terminate abruptly. Therefore, forced unwrapping should be used sparingly, and only when you are absolutely sure the optional contains a valid value. It's important to weigh the convenience of this method against the potential for runtime errors. The primary risk of using forced unwrapping is that it can lead to runtime crashes if the optional is nil. This is particularly dangerous in real-world applications where data might be incomplete or unavailable. For instance, if you're retrieving user data from a server and the server returns an unexpected response, the optional might not have a value, but your code could still attempt to unwrap it, causing the app to crash. This makes forced unwrapping a risky practice, especially when dealing with user input or external data sources. Instead of relying on forced unwrapping, it's better to use safer methods like optional binding to check for the presence of a value before accessing it. By doing so, you can handle nil cases gracefully and avoid unexpected crashes. There are specific scenarios where forced unwrapping might be appropriate, but they are limited. For example, if you are initializing a variable in a controlled environment where you know the value will be present, such as during setup or configuration, you might use forced unwrapping. Another case is when you are working with a variable that has been explicitly set to a non-nil value, and you are certain it won't change. However, even in these situations, it's crucial to ensure that the optional is not nil. If there's any doubt, it's safer to use optional binding or provide a default value. Forced unwrapping should never be used as a default approach, as it can lead to unpredictable behavior and crashes. Always consider the context and potential for nil values before deciding to use this method. To safely access the value of an optional, Swift provides two main techniques: optional binding and nil coalescing. Optional binding allows you to check if an optional has a value, and if so, assign it to a constant or variable for use. This is done using the if-let or guard-let syntax, which ensures that the value is present before proceeding. Nil coalescing, on the other hand, provides a default value if the optional is nil, making it useful for cases where a fallback is acceptable. For example, you might use username, guest, to assign a default name if the optional is empty. By using these methods, you can handle nil values gracefully and avoid runtime errors. These practices not only make your code more robust, but also improve readability and maintainability. In summary, optionals are a fundamental aspect of Swift programming that help manage the presence or absence of values. While forced unwrapping can be convenient in certain situations, it should be used with caution due to the risk of crashes. Instead, developers are encouraged to use optional binding and nil coalescing to handle nil values safely. These techniques promote more reliable code by ensuring that all possible cases are accounted for. By understanding and applying these principles, you can write Swift code that is both safe and efficient. Remember, the goal is to anticipate potential issues and handle them proactively, rather than relying on assumptions that might lead to runtime errors. Lazy initialization is a technique where the creation of a property is postponed until the moment it is first accessed. This approach is particularly useful in scenarios where initializing a property might be computationally expensive or dependent on external factors. For example, if a property requires loading a large file from disk or establishing a network connection, deferring its initialization until it is actually needed can save resources and improve performance. By delaying the initialization, we avoid unnecessary operations that might not even be used during the object's lifetime. This is especially valuable in applications where certain features or data are optional or only required under specific conditions. In Swift, the lazy keyword is used to declare a property that is initialized only when it is first accessed. The syntax for a lazy property involves placing the lazy keyword before the property declaration, followed by a closure that returns the initial value. For instance, the code lazy var property name type equals demonstrates how a lazy property is defined. The closure is executed only once when the property is first accessed, and the result is stored for subsequent accesses. It is important to note that the lazy keyword can only be applied to variables declared with the var keyword, not with let constants, because let constants are immutable and must be initialized at the time of declaration. The difference between eager and lazy initialization lies in the timing of property initialization. Eager initialization occurs when the object is created, meaning all properties are set up immediately, regardless of whether they are used later. In contrast, lazy initialization delays the setup of a property until the first time it is accessed. This distinction is crucial for performance optimization. For example, if a property requires a time-consuming operation, like parsing a large data set, initializing it eagerly would waste resources if the property is never used. Lazy initialization ensures that such operations are performed only when necessary, reducing initial overhead and improving efficiency. Lazy initialization is particularly beneficial in several scenarios. First, it is ideal for expensive operations such as loading large data sets from disk, performing complex calculations, or making network requests. By deferring these tasks, the application can remain responsive and efficient. Second, it is useful for properties that depend on external factors, such as user preferences, device sensors, or configuration files, which might not be available at the time of object creation. Finally, lazy initialization is well suited for optional properties that may not be needed during the object's lifecycle. For instance, a feature that is only activated under specific conditions can be initialized lazily, ensuring resources are only allocated when required. Let me walk through an example of lazy initialization in Swift. Consider a class called DataLoader, which has a lazy property named data. The code lazy var data string equals return load from disk defines this property. When the data property is first accessed, the closure is executed, and the result of the load from disk function is stored. This function might read a file or fetch data from a remote server. By using lazy initialization, the DataLoader class avoids loading the data until it is actually needed, which can significantly improve performance. Subsequent accesses to data will directly return the already loaded value, eliminating the need for repeated computations or resource-intensive operations. While lazy initialization offers many benefits, there are important considerations to keep in mind. One key issue is thread safety. By default, lazy properties are not thread safe, meaning that if multiple threads access the property simultaneously, there is a risk of race conditions or inconsistent states. Developers must handle synchronization manually in such cases. Additionally, lazy initialization should not be used for properties that require complex setup or dependencies that might change after the object is created. Finally, it is crucial to ensure that lazy properties are accessed only after the object has been fully initialized. Accessing them too early, such as in an initializer, can lead to unexpected behavior or runtime errors. In summary, lazy initialization is a powerful tool for optimizing performance by deferring resource-heavy tasks until they are needed. It is particularly useful for expensive operations, external dependencies, and optional properties. However, it should be used with care, as it comes with limitations such as thread safety concerns and the need for proper initialization order. By understanding when and how to apply lazy initialization, developers can create more efficient and responsive applications. Always evaluate the trade-offs and ensure that lazy properties are implemented in a way that aligns with the specific needs of your code base. Functional programming is a programming paradigm that prioritizes the use of immutable data and pure functions to build software. Unlike traditional approaches that rely on changing state and mutable data, functional programming focuses on expressing computations through mathematical functions. This means that instead of writing a series of steps to achieve a result, we emphasize expressions that evaluate to values. The core principles of functional programming include immutability, where data remains unchanged after creation, first-class functions, which allow functions to be treated as values, and higher-order functions, which can take other functions as parameters or return them. Swift supports these concepts through features like closures, which are self-contained blocks of code, and higher-order functions such as map, filter, and reduce. These tools enable developers to write concise, expressive, and maintainable code by leveraging functional patterns. Immutability is a foundational concept in functional programming, ensuring that once a value is created, it cannot be altered. This approach reduces unexpected side effects and makes code more predictable. Pure functions are another key principle, where the output of a function depends solely on its input parameters, with no reliance on external state. This characteristic makes pure functions easier to test and reason about. Higher order functions take other functions as arguments or return them as results, allowing for powerful abstractions and code reuse. For example, a function can accept a closure to define specific behavior dynamically. Recursion is a technique where a function calls itself to solve a problem, often used to replace loops in functional programming. Together, these concepts form the backbone of functional programming, enabling developers to create robust and scalable applications. Closures in Swift are like anonymous functions that can be passed around and used as values. They are particularly useful for encapsulating functionality that can be executed later. The syntax for a closure is straightforward. It starts with curly braces, followed by parameters and a return type, and ends with the keyword in to separate the parameters from the body. For instance, a simple closure that adds two numbers might look like $0 plus $1. What makes closures powerful is their ability to capture and store references to variables and constants from their surrounding context. This means a closure can access and modify values from the environment in which it was defined, even if that environment has since gone out of scope. This feature is especially useful for tasks like asynchronous programming or customizing behavior in higher order functions. Higher order functions are essential tools in functional programming, allowing developers to manipulate collections of data in a declarative way. The map function transforms each element in a collection by applying a given closure, making it easy to perform operations like scaling numbers or converting strings. The filter function selects elements that meet a specific condition, such as finding all even numbers in an array. The reduce function combines elements into a single value, like summing all numbers or concatenating strings. For example, numbers.map $02 multiplies each element by 2, demonstrating how these functions can simplify complex operations. By using higher order functions, developers can write more readable and maintainable code, reducing the need for verbose loops and boilerplate. A pure function is one that always produces the same output for the same input and has no side effects. This means it does not modify any external state or variables, making it highly predictable. For instance, a function that adds two numbers is pure because it does not alter any data outside its scope. In contrast, a function that updates a global variable or performs I/O operations introduces side effects, which can lead to bugs and make testing difficult. Functional programming emphasizes avoiding side effects to ensure code is easier to debug and test. By designing functions to be pure, developers can create systems that are more reliable and modular. As each function's behavior is isolated and well-defined, immutability in Swift is enforced through the use of the let keyword, which declares constants that cannot be modified after initialization. This approach prevents accidental changes to data, reducing the risk of bugs. Collections like arrays and dictionaries can also be made immutable, ensuring their contents remain fixed once created. Additionally, Swift's struct types are value types, meaning they are copied when assigned or passed around, further reinforcing immutability. This design choice helps prevent unintended side effects, as changes to one instance do not affect others. By leveraging immutability, developers can write safer code that is easier to reason about, especially in concurrent or parallel environments where shared state can lead to conflicts. Functional patterns in Swift include currying, lazy evaluation, and memoization, each offering unique advantages. Currying transforms a function with multiple parameters into a sequence of functions, each taking a single argument. This allows for partial application, where a function can be called with some arguments and later completed with others. Lazy evaluation defers the execution of a computation until its result is needed, improving efficiency by avoiding unnecessary work. For example, Swift's lazy sequences only process elements when accessed. Memoization is a technique that caches the results of expensive function calls, so repeated calls with the same arguments can reuse the stored result. These patterns help optimize performance and simplify complex logic, making functional programming even more powerful in Swift. The benefits of functional programming are numerous, making it a valuable approach for modern software development. By focusing on pure functions and immutability, code becomes easier to reason about, as each function's behavior is isolated and predictable. This modularity enhances testability, as individual components can be tested independently without relying on external state. Immutability also simplifies parallelization, as shared data cannot be modified concurrently, reducing the risk of race conditions. Additionally, functional programming reduces bugs caused by unexpected state changes, leading to more stable and maintainable applications. These advantages make functional programming an excellent choice for building scalable and reliable software, especially in environments where concurrency and correctness are critical. While functional programming offers many advantages, it also presents challenges that developers must navigate. One common difficulty is the learning curve for those accustomed to imperative programming styles, as functional concepts like immutability and higher-order functions require a shift in mindset. Performance considerations can also arise, as immutability often involves creating new data structures rather than modifying existing ones, which may lead to increased memory usage or processing overhead. Additionally, functional programming may not be the best fit for applications heavily reliant on stateful operations or I/O-bound tasks, where imperative approaches might be more straightforward. However, by understanding these challenges and leveraging Swift's hybrid capabilities, developers can find a balance between functional and object-oriented programming to suit their specific needs. In conclusion, functional programming provides a powerful set of tools for writing clean, maintainable, and scalable code. Swift's support for closures, higher-order functions, and functional patterns makes it an excellent language for exploring these concepts. While functional programming is not a one-size-fits-all solution, it complements object-oriented programming by offering alternative ways to structure and manage code. By applying functional principles to real-world problems, developers can create software that is more predictable, testable, and efficient. The key is to understand when and how to use these techniques, combining them with other paradigms to build robust and flexible solutions. Practice and experimentation are essential to mastering functional programming and unlocking its full potential in Swift. Higher-order functions are a fundamental concept in Swift programming. These are functions that can accept other functions as parameters or return them as results. This capability allows for a more flexible and powerful approach to coding. In Swift, functions are first-class citizens, meaning they can be passed around just like any other value. This makes it possible to implement functional programming patterns, which can lead to more concise and expressive code. For example, functions like map, filter, reduce, and compact map are all higher-order functions functions that operate on collections. Map transforms each element. Filter selects elements based on a condition. Reduce aggregates values into a single result. And compact map converts elements while removing nil values. These functions enable developers to write elegant and readable code by abstracting common operations. Closures are self-contained blocks of code that can be passed around and used within your code. Unlike functions, which have names and can be called directly, closures are anonymous and can be assigned to variables or passed as arguments. This makes them incredibly versatile. Closures can also capture and store references to any constants or variables from their surrounding context, which means they can access and modify values from the environment in which they are defined. This feature is particularly useful for creating closures that adapt to their surroundings. For instance, a closure might capture a variable from an outer scope and use it later, even if that variable is no longer in existence. This ability to capture context is what makes closures so powerful and flexible in Swift. The syntax for closures in Swift has two main forms. The full syntax is parameters return type in statements, where you explicitly define the parameters, return type, and the code block. For example, a closure that adds two integers would look like a int b, int in return a plus b. However, Swift provides a shorthand syntax for simpler closures, using $0, $1, and so on to represent the parameters. For instance, $0 plus $1 is a concise way to write a closure that adds two values. Another example is $2, which doubles a given value. This shorthand makes closures more readable and easier to write, especially for short, inline operations. Understanding both syntaxes allows developers to choose the most appropriate form for their specific use case. Trailing closures are a convenient feature in Swift that allows you to write a closure after a function call, especially when it is the last parameter. This improves readability by reducing the need for extra parentheses. For example, instead of writing numbers.map $2, you can write numbers.map $2. This syntax is particularly useful when working with complex functions that have multiple parameters, as it keeps the code cleaner and more focused on the closure's logic. Trailing closures are commonly used in Swift for methods like map, filter, and sorted, where the closure is the final argument. This style of writing code makes it easier to understand the flow of data and operations, especially in longer chains of function calls. Escaping closures are closures that outlive the function they are passed to. This means they can be stored and called later, even after the function that created them has finished executing. Because of this, escaping closures must be explicitly marked with the @escaping attribute in the function signature. For example, a function that fetches data and uses a completion handler would be declared as func fetch data completion. @escaping data void. The @escaping keyword informs the compiler that the closure may be used outside the scope of the function, which is necessary for scenarios like asynchronous operations or storing closures for later execution. Without this attribute, the compiler would prevent the closure from being stored, ensuring safe and predictable code behavior. Closures and functions in Swift serve different purposes. Functions are named and can be called directly, making them ideal for reusable logic that is used in multiple places. Closures, on the other hand, are anonymous and can be assigned to variables, passed as arguments, or used inline. This makes closures perfect for short, specific operations that are tied to a particular context. For example, a function might handle a general task like calculating a tax rate, while a closure might be used to sort an array of strings. Understanding when to use each is key to writing efficient and maintainable code. Functions provide clarity and reusability, while closures offer flexibility and conciseness, especially when working with higher-order functions. Common higher-order functions in Swift include map, filter, reduce, and compact map. Map is used to transform each element in a collection, such as doubling all numbers in an array. Filter selects elements that meet a specific condition, like finding all even numbers. Reduce aggregates elements into a single value, such as summing all numbers in an array. Compact map is similar to map, but also filters out nil values, making it useful for converting elements that might produce optional results. These functions are essential for working with collections and allow developers to express complex operations in a simple and declarative way. By mastering these tools, programmers can write more efficient and readable code that is easier to maintain and understand. Let's look at some practical examples of closures in action. For sorting, you might use a closure like name sort $0, $1 which compares two strings and sorts them in alphabetical order. When filtering even numbers, a closure such as numbers filter $0% 2 = 0 would return an array of all even values. For reducing an array, a closure like numbers reduce $0 plus $1 starts with an initial value of 0 and accumulates the sum of all elements. These examples demonstrate how closures can be used to perform specific tasks inline, making the code more concise and expressive. By leveraging closures in these ways, developers can create more dynamic and adaptable programs. Closures have the ability to capture constants and variables from their surrounding context, which is a powerful feature, but also requires careful handling. For instance, if a closure captures a reference to self, it might create a retained cycle where two objects hold strong references to each other, preventing them from being deallocated. To avoid this, Swift provides the weak and unowned keywords. Weak references do not increase the reference count and are used for optional values, while unowned references are used for non-optional values that are guaranteed to exist. An example of this is when adding a closure to a button's action. Button, add target self, weak self in self. Do something which ensures the closure does not retain a strong reference to self, preventing memory leaks. In conclusion, higher order functions and closures are essential tools in Swift programming. They allow for concise, expressive, and maintainable code by abstracting common operations and enabling flexible function composition. Mastering these concepts can significantly improve code readability and reusability, making it easier to work with complex data transformations. By practicing with functions like map, filter, and reduce, developers can leverage functional programming patterns to write more efficient and elegant solutions. As you continue your Swift journey, remember that closures are not just a syntax feature, but a powerful paradigm that can transform the way you approach problem solving in your code. Error handling in Swift is a critical aspect of writing reliable and resilient code. It allows developers to manage unexpected conditions that may arise during program execution. These conditions can range from invalid user input to failed network requests or corrupted data. Swift provides a structured approach to error handling using the keywords do, try, and catch. This structure ensures that errors are not ignored, but are instead addressed in a clear and organized manner. By incorporating error handling, you can prevent crashes, improve user experience, and make your code more maintainable. Functions, methods, and initializers can all generate errors, and Swift's type system ensures that these errors are explicitly handled, making your code safer and more predictable. The basic structure of error handling in Swift revolves around the do, try, and catch keywords. A do block is used to enclose code that may throw an error. When a function or method can throw an error, you mark it with the try keyword before calling it. This signals to the compiler that the code may need to handle an error. The catch block is where you handle the error. It can be used to catch specific error types or a generic error. For example, if a function called someThrowingFunction throws an error, the do block will execute until it encounters the try statement. If an error occurs, the code jumps to the catch block, where you can log the error or take corrective action. This structured approach ensures that errors are handled in a controlled and readable way. Functions in Swift can be designed to throw errors by using the throws keyword in their declaration. This indicates that the function may encounter an error during its execution. For instance, a function that loads a file from a given path might throw an error if the file is missing or inaccessible. When a function throws an error, it must be called within a try statement. The throw keyword is used to explicitly signal an error, such as when invalid data is encountered. This mechanism is particularly useful in scenarios like file I/O, network requests, or data parsing, where failures are common. By marking functions as throwing, you make it clear to other developers that the function may not always succeed, encouraging them to handle errors appropriately. Catching specific errors allows for more precise and meaningful error handling. Instead of using a generic catch block, you can specify the exact error type you want to handle. For example, if a function can throw a custom error type like file error invalid input, you can create a catch block that responds specifically to that case. This approach enables you to provide tailored messages or actions, such as prompting the user for valid input or logging detailed diagnostics. In addition to specific cases, a generic catch block can handle any remaining errors, ensuring that no error goes unaddressed. This level of specificity improves both the user experience and the debugging process, as errors are clearly identified and handled. Custom error types in Swift are defined using enums that conform to the error protocol. This allows you to create domain-specific errors that are both readable and expressive. For example, an enum called network error can have cases like invalid URL or connection failed, each representing a distinct failure scenario. By defining custom errors, you avoid using vague or generic error messages, making your code easier to understand and maintain. Custom errors also enable you to provide additional context when throwing an error, such as including a description or associated values. This practice is especially useful in larger projects where clear error communication is essential for collaboration and debugging. Implementing custom errors involves integrating them into throwing functions, where they can be thrown when specific conditions are met. For instance, a function that connects to a URL might check if the URL is valid and throw a network error invalid URL if it is not. This approach allows you to encapsulate error logic within the function, making it easier to manage and reuse. When combined with the do-catch structure, custom errors enable you to handle different failure scenarios gracefully. For example, you can catch a specific network error case and display a user-friendly message, while a generic catch block handles unexpected issues. This integration ensures that errors are both meaningful and actionable. Error propagation in Swift allows errors to travel up the call stack, giving higher-level functions the responsibility to handle them. This is achieved by marking functions with the throws keyword, which indicates that they can throw errors. For example, a function called process file might call another function like load file, which can throw an error. Instead of handling the error immediately, process file can propagate it to the caller, who can then decide how to respond. This approach reduces the need for nested do-catch blocks, keeping the code cleaner and more modular. It also encourages a separation of concerns, where each function handles errors at the appropriate level of the program. Swift provides 2 additional ways to handle errors: try and try. The try operator converts the result of a throwing function into an optional. If an error is thrown, the result becomes nil, allowing you to handle the absence of a value gracefully. This is useful for non-critical errors, where you can proceed without the result. On the other hand, try forces the unwrapping of the result But if an error is thrown, the program will crash. This should be used only in contexts where you are certain the function will not fail, such as during initialization. Understanding when to use try or try is essential for balancing safety and convenience in your code. In conclusion, error handling is a cornerstone of building robust and reliable Swift applications. The do-try-catch structure provides a clear and structured way to manage errors, ensuring that they are not overlooked. Custom errors enhance code readability and maintainability by allowing you to define meaningful error types specific to your application. Mastering error propagation enables you to handle errors at the appropriate level of your code, reducing complexity. Finally, understanding when to use try, or explicit error handling allows you to write safer and more efficient code. By incorporating these practices, you can create applications that are resilient, user-friendly, and easier to debug. Concurrency allows multiple tasks to run independently and efficiently, which is essential for building responsive and high-performance applications. In Swift 5.5, the introduction of async and await has revolutionized how we handle asynchronous code, making it more intuitive and easier to manage. These keywords enable developers to write asynchronous functions that look and behave like synchronous code, reducing complexity. Key concepts such as async functions, which are marked with the async keyword, and await expressions, which pause execution until a result is ready, form the foundation of this approach. Task management ensures that these operations are handled without blocking the main thread, which is crucial for maintaining smooth user experiences. The benefits of using concurrency in Swift include improved performance through efficient resource utilization, increased responsiveness by avoiding delays in the main thread, and better scalability for handling complex and large-scale applications. The async and await syntax in Swift provides a straightforward way to work with asynchronous functions. The async keyword is used to declare a function that performs an asynchronous operation, such as fetching data from a network or reading from a file. This function returns a value that is available at a later time, and the await keyword is used to pause the execution of the current function until that value is ready. For example, a function like funcFetchDataAsync data would fetch data asynchronously and return it once available. This approach simplifies code that previously relied on nested completion handlers or closures, which could become difficult to read and maintain. By using a sync and await, developers can write code that flows linearly, making it easier to understand and debug. This syntax also aligns with modern programming practices, reducing the risk of errors that often arise from callback-based patterns. Async functions in Swift are designed to perform operations that take time, such as network requests or disk I/O, without blocking the main thread. When you mark a function with the async keyword, it signals that it can be paused and resumed later, allowing the program to continue executing other tasks. This is particularly useful for maintaining a responsive user interface. Additionally, Swift provides the task type to launch independent asynchronous tasks, which can run concurrently. For instance, task await fetch data creates a new task that executes the fetch data function asynchronously. This separation of tasks ensures that long-running operations do not interfere with the main thread, preventing the application from becoming unresponsive. By leveraging async functions and tasks, developers can structure their code to handle multiple operations efficiently, improving the overall performance and user experience of their apps. Handling errors in asynchronous code requires a structured approach, and Swift provides do-catch blocks to manage these scenarios. When working with async functions that can throw errors, the try keyword is used to indicate that the function might throw an error. For example, a function like funcFetchData async throws data would need to be called with try await to handle potential errors. The do-catch block allows developers to catch and handle these errors gracefully, ensuring that the application can respond appropriately. This is especially important in scenarios where network requests or file operations might fail. Additionally, the rethrows keyword can be used in async closures to propagate errors from the closure to the caller, maintaining a clear error handling chain. By incorporating these mechanisms, developers can create robust and reliable asynchronous code that is easier to maintain and debug. Concurrency patterns in Swift offer various tools to manage complex asynchronous operations. The async let keyword allows developers to launch multiple tasks concurrently, enabling efficient execution of independent operations. For example, a Async let data equals fetch data, and async let image equals download image can both run at the same time, improving performance. Actors provide a way to encapsulate shared state and prevent race conditions by ensuring that only one task can access the state at a time. This is crucial for maintaining data integrity in multi-threaded environments. Async sequences allow iteration over asynchronous data streams, such as reading lines from a file or processing network data in real time. Finally, task groups, like with Task Group, help manage parallel workloads by grouping multiple tasks and handling their results collectively. These patterns empower developers to build scalable and efficient applications that can handle a wide range of asynchronous scenarios. Following best practices for async and await is essential for writing clean and maintainable code. One key principle is to avoid mixing synchronous and asynchronous code unnecessarily, as this can lead to unpredictable behavior and performance issues. For example, calling an async function from a synchronous context without proper handling can cause deadlocks or crashes. Using the @main_actor attribute ensures that UI updates occur on the main thread, preventing race conditions and ensuring a smooth user experience. Developers should prefer async and await over completion handlers for clarity, as the former provides a more straightforward and readable structure. Testing async code with xctest and its async methods, such as xctest cases async functions, helps verify that the code behaves correctly under various conditions. By adhering to these practices, developers can create more reliable and efficient applications that are easier to maintain and scale. Async and await in Swift have transformed the way developers write asynchronous code, making it simpler and more intuitive. By leveraging concurrency, developers can significantly improve the performance and responsiveness of their applications, ensuring a better user experience. Following best practices, such as avoiding mixed sync and async code, and using actors to manage shared state, helps prevent common pitfalls like deadlocks or race conditions. For more complex scenarios, exploring advanced topics like actors and task groups can unlock additional capabilities and efficiency. As Swift continues to evolve, mastering these concepts will be crucial for building modern, scalable applications that meet the demands of today's users. Threads are the fundamental building blocks of execution within a program. They allow different parts of a program to run independently, enabling what we call concurrency. This means that multiple tasks can be processed at the same time, which is crucial for efficient application performance. However, when a program runs on a single thread, long-running operations can cause the application to freeze, making it unresponsive to user interactions. This is why multi-threading is essential. It allows the program to handle multiple tasks simultaneously, improving both performance and the overall user experience. By distributing work across multiple threads, applications can remain responsive even during intensive operations. Grand Central Dispatch, or GCD, is Apple's powerful framework designed to manage concurrency in applications. It simplifies the process of writing concurrent code by abstracting the complexities of low-level thread management. Instead of manually creating and managing threads, developers can rely on GCD to handle these tasks efficiently. GCD uses queues to organize and execute tasks, which act as a central hub for scheduling work. These queues can be serial, processing tasks one at a time, or concurrent, allowing multiple tasks to run simultaneously. In Swift, GCD is seamlessly integrated through the Foundation framework, making it accessible for developers to implement concurrency without additional setup. GCD provides several types of queues, each with a specific purpose. Serial queues execute tasks in the order they are added, ensuring that only one task runs at a time. This is ideal for tasks that require strict sequencing, such as updating shared resources. Concurrent queues, on the other hand, allow multiple tasks to run simultaneously, making them suitable for CPU-intensive operations. The main queue is a special serial queue that runs on the main thread, and it is the only place where UI updates should occur. Global queues are predefined concurrent queues with varying priority levels, such as background, utility, and default. These queues are optimized for different types of tasks, allowing developers to choose the appropriate one based on the workload. When dispatching work in Swift, it's important to understand the difference between asynchronous and synchronous execution. The dispatch queue global async method is used to offload tasks to a background queue, ensuring that they do not block the main thread. This is particularly useful for operations like data processing or network requests. Conversely, the dispatch queue main async method is used to return to the main thread for UI updates, which must always occur on the main queue. The async keyword allows tasks to run concurrently, while sync blocks the current thread until the task completes. However, using sync can lead to deadlocks if not handled carefully, so it's best reserved for situations where immediate results are required. Always avoid performing heavy computations on the main thread, as this can make the application unresponsive. Synchronization is a critical aspect of concurrent programming, and GCD provides tools to manage it effectively. The sync method should be used with caution, as it can lead to deadlocks if two threads are waiting for each other to complete. A barrier is a special type of task that ensures exclusive access to a resource, preventing other tasks from executing until the barrier is complete. This is particularly useful when modifying shared data. Additionally, Dispatch Group allows developers to track the completion of multiple tasks, making it easier to coordinate complex operations. When working with shared resources, careful synchronization is necessary to prevent race conditions and ensure data integrity. By leveraging these tools, developers can create robust and reliable concurrent code. Compared to traditional thread management, GCD offers significant advantages. While threads require manual creation, configuration, and management, GCD abstracts these details, reducing the amount of boilerplate code needed. Frameworks like Thread or NS Operation demand more overhead, as developers must handle thread safety, priority settings, and synchronization manually. GCD simplifies this process by providing higher-level abstractions that handle these complexities behind the scenes. This makes it easier for developers to write efficient and maintainable code. For modern Swift development, GCD is the preferred choice due to its simplicity, performance, and integration with the Foundation framework. It allows developers to focus on solving problems rather than managing threads. Let's look at an example of an asynchronous task using GCD. In this snippet, we start by dispatching a task to a global queue with a background quality of service. This ensures that the task runs in the background, away from the main thread. Inside this block, we perform the necessary background work, such as processing data or fetching information from a network. Once the background task is complete, use dispatch sync to return to the main thread and update the user interface. This pattern is essential for maintaining a responsive user experience, as it separates long-running operations from UI updates. By leveraging GCD's dispatch queues, developers can efficiently manage concurrency without the pitfalls of manual thread management. To ensure optimal performance and avoid common pitfalls, it's important to follow best practices when working with GCD. First, always keep the main thread free for UI updates, as blocking it can lead to unresponsiveness. For CPU-intensive tasks, use global queues to offload work to background threads. Avoid overusing sync, as it can introduce deadlocks if not used carefully. Instead, prefer a sync for non-blocking operations. Finally, thoroughly test concurrency logic to identify and resolve issues such as race conditions or deadlocks. These practices will help create applications that are both efficient and reliable, ensuring a smooth experience for users. In conclusion, threading and GCD are fundamental to building responsive and efficient applications. GCD simplifies the complexities of concurrency by providing a high-level abstraction that manages threads behind the scenes. Understanding the different queue types, such as serial, concurrent, main, and global, allows developers to structure their code effectively. Synchronization mechanisms like sync, barrier, and dispatch group are essential for managing shared resources and coordinating tasks. By following best practices and avoiding common mistakes, developers can harness the power of GCD to create robust and scalable applications. Applying these concepts will help ensure that your Swift programs are both performant and user-friendly. SwiftUI is a declarative framework designed to make building user interfaces in Swift more intuitive and efficient. Unlike traditional imperative approaches, where you tell the system exactly how to build the UI, SwiftUI allows you to describe what the UI should look like, and the framework handles the rest. This declarative syntax not only simplifies the code, but also reduces the amount of boilerplate required, making development faster and less error-prone. One of the standout features of SwiftUI is its ability to unify the development process across multiple Apple platforms, including iOS, macOS, tvOS, and watchOS. This means developers can write code once and deploy it across various devices, ensuring a consistent user experience. Additionally, SwiftUI integrates seamlessly with Xcode, offering live previews that update in real time as you make changes. This immediate feedback loop helps you visualize and refine your UI without constantly running the app, saving time and improving productivity. The key components of SwiftUI are essential for creating dynamic and visually appealing interfaces. Views form the foundation, providing elements like text, images, buttons, toggles, sliders, and more. These views are the building blocks that you combine to create the UI. Layouts such as HStack, VStack, CStack, and Spacer allow you to arrange these views in a structured and responsive manner. For example, HStack places elements side by side horizontally, while VStack stacks them vertically. CStack layers views on top of each other, and Spacer helps distribute space between elements. State management is another critical aspect, with tools like @state, @binding, and @observed object. @state is used for simple, local state changes within a view, while @binding creates a two-way connection between views. @observed object is ideal for managing complex state that exists outside the view, such as in a view model. Finally, modifiers like font, padding, background, and on-tap gesture allow you to customize the appearance and behavior of views. These modifiers are chainable, enabling you to apply multiple styles and interactions to a single view with ease. Building a simple UI in SwiftUI starts with creating a struct that conforms to the view protocol. This struct defines the layout and behavior of the interface. For example, a basic counter app might use @state to track the count value, which is a mutable property that updates the UI when changed. The body of the struct contains the actual UI elements, such as a button that increments the count and a text view that displays the current value. In the provided example, the button has an action that increases the count by 1, and the text view shows the updated value. This simple structure illustrates how SwiftUI combines state management with UI elements to create interactive interfaces. By leveraging @state, developers can ensure that the UI automatically updates whenever the underlying data changes, eliminating the need for manual updates. This approach not only streamlines development, but also makes the code more readable and maintainable. Modifiers in SwiftUI are powerful tools for customizing views and enhancing their functionality. For instance, the font modifier adjusts the text size, allowing you to use predefined styles like large title or body, or even specify a custom font. The padding modifier adds space around a view, improving readability and aesthetics. By default, it adds a standard amount of padding, but you can also specify different values for top, bottom, leading, and trailing edges. The background modifier lets you apply a color or image to the back of a view, creating visual hierarchy and depth. Lastly, the on-tap gesture modifier enables you to define actions that occur when a user taps a view, such as navigating to another screen or triggering an animation. These modifiers are not limited to the examples listed. They can be combined in creative ways to achieve complex designs. Their declarative nature means you can chain multiple modifiers to a single view, making the code concise and expressive. Understanding state and data flow is crucial for effective SwiftUI development. At state is used for managing simple, local state within a view, such as the state of a toggle or the value of a counter. When the state changes, the view automatically updates, ensuring the UI reflects the latest data. At binding, on the other hand, creates a two-way connection between a view and a shared state, often used when a child view needs to update a value in a parent view. This is particularly useful for forms or settings where changes in one part of the UI affect another. At observed object is reserved for more complex scenarios where the state is managed outside the view, such as in a view model or a shared data source. This allows multiple views to observe and react to changes in the same data, promoting code reuse and separation of concerns. By choosing the right state management tool for each situation, developers can create scalable and maintainable applications. Following best practices in SwiftUI ensures that your code remains clean, efficient, and easy to maintain. Keeping views small and focused on a single responsibility makes them easier to test, debug, and reuse. For example, a view should handle only its own UI and state, delegating complex logic to other components. Using at state for UI-driven changes, such as button presses or slider movements, keeps the view self-contained and responsive. At binding is ideal for scenarios where a view needs to share or update a value with another view, such as a settings toggle that affects multiple sections of the app. However, it's important to avoid overusing an observed object unless necessary, as it introduces additional complexity. By adhering to these guidelines, designs, developers can create applications that are not only functional, but also scalable and easier to evolve over time. In summary, SwiftUI provides a modern, declarative approach to UI development that simplifies the process while offering powerful tools for building cross-platform applications. Mastering views, modifiers, and state management is essential for creating dynamic and interactive interfaces. Practicing with live previews allows you to see changes in real time, accelerating the development cycle as you become more comfortable with the basics. Exploring advanced topics like navigation, animations, and data binding will further expand your capabilities. SwiftUI's flexibility and integration with Xcode make it an excellent choice for developers looking to streamline their workflow and deliver high-quality user experiences across Apple platforms. By continuing to experiment and refine your skills, you'll be well equipped to tackle even the most complex UI challenges. Welcome to this session on advanced SwiftUI views. Today, we'll explore concepts that go beyond the basics of SwiftUI, focusing on how to create more sophisticated and maintainable user interfaces. Custom views and modifiers are essential tools for building complex applications, allowing developers to encapsulate functionality and reuse code efficiently. By mastering these elements, you'll be able to create more scalable and elegant solutions. Our key objectives today include learning how to build reusable components, manage state effectively, and implement animations to enhance user interactions. Let's dive into the details. Creating reusable views is a cornerstone of efficient SwiftUI development. By defining custom views using struct declarations, you can encapsulate complex UI logic into single, manageable units. This approach not only improves code readability, but also ensures consistency across your application. In addition to views, custom modifiers allow you to apply consistent styling across multiple elements, reducing redundancy. For example, you can create a modifier that adjusts font size, color, and padding all in one place. Combining modifiers enables even more powerful transformations, such as applying a series of animations or layout adjustments. Understanding how to chain and customize these modifiers is crucial for building dynamic and responsive interfaces. State management is a critical aspect of SwiftUI, and it requires a clear understanding of the available tools. The at-state property wrapper is used for managing local view state, such as tracking user input or toggling visibility. When you need to synchronize data between views, at-binding provides a two-way connection, ensuring that changes in one view are reflected in another. For more complex scenarios, at observed object and at published work together to share state across multiple views, often in conjunction with the combine framework. This approach is ideal for applications where data needs to persist beyond a single view. By leveraging these tools, you can create applications that are both responsive and maintainable. Animations and transitions bring life to your user interface, making interactions more intuitive and engaging. The animation modifier allows you to apply smooth transitions to changes in your view hierarchy, such as resizing or repositioning elements. You can further customize these animations using functions like spring, timing curve, and delay to create unique effects. For example, a spring animation might mimic a bouncy effect, while a timing curve can control the acceleration and deceleration of an animation. Transitions are also essential for handling view additions and removals, such as when navigating between screens or presenting modals. Mastering these techniques will help you create visually appealing and polished applications. Dynamic layouts are essential for building responsive user interfaces that adapt to different screen sizes and orientations. The Geometry Reader view allows you to access the dimensions and position of a parent view, enabling you to calculate layout parameters on the fly. This is particularly useful for creating layouts that adjust based on user input or device constraints. By combining frame, padding, and alignment modifiers, you can fine-tune the placement and sizing of elements. Additionally, stacking views using H-stack, V-stack, and Z-stack allows you to create layered designs that balance complexity with clarity. These techniques are vital for ensuring your app looks great on all devices. Chaining modifiers is a powerful way to achieve intricate UI effects, but it requires careful attention to order and priority. Each modifier in a chain can affect the behavior of the previous one, so understanding their sequence is crucial. For instance, applying a rotation modifier before a translation modifier might produce a different result than the reverse. Conflicts or overlaps can arise when multiple modifiers interact unexpectedly. So debugging these issues often involves isolating parts of the chain to identify the source. By practicing with different combinations and observing their outcomes, you'll develop a deeper intuition for how modifiers work together to shape your user interface. Optimizing performance in SwiftUI is essential for creating smooth and efficient applications. One key strategy is to avoid unnecessary view rebuilds by using at state and at binding appropriately. When a view's state changes, SwiftUI only rebuilds the affected parts, but improper use of these properties can lead to excessive updates. The @published property wrapper, paired with Combine, allows for efficient state updates across views, reducing the overhead of manual refreshes. Techniques like lazy loading and conditional rendering also play a role in performance, ensuring that only necessary components are created or updated. By applying these practices, you can build applications that are both fast and scalable. To recap, mastering custom views and modifiers is fundamental to unlocking SwiftUI's full potential, enabling you to build more efficient and maintainable code. Advanced state management techniques ensure that your applications can handle complex data flows while remaining responsive and scalable. Animations and dynamic layouts enhance the user experience by making interactions more intuitive and visually appealing. As you continue exploring SwiftUI, remember that these concepts are not just tools, but foundational principles that will shape the quality of your applications. Keep experimenting and refining your approach to create exceptional user experiences. Core Data is a powerful framework designed to help developers manage data persistence in iOS and macOS applications. It provides an object-oriented approach to data modeling, allowing you to define your data structure in a visual interface. This framework not only stores data, but also enables efficient retrieval, modification, and management of that data. By using Core Data, you can avoid writing boilerplate code for data handling, making your applications more scalable and maintainable. It acts as a bridge between your app's data and the underlying storage mechanisms, ensuring a seamless experience for developers and users alike. The architecture of Core Data consists of 3 key components that work together to manage data. The data model serves as the blueprint for your application's data structure, defining entities, attributes, relationships. These entities represent objects in your app, such as users or products, while attributes describe their properties. The managed object context functions as a temporary workspace where you can create, modify, and delete data before saving it to the persistent store. The persistent store is the actual storage mechanism, which can be in the form of SQLite databases, XML files, or binary files. Together, these components ensure that your data is both flexible and reliable. Setting up core data in Xcode is a straightforward process that begins when you create a new project. Xcode provides an option to enable core data, which automatically generates the necessary files. The XCDataModeled file is where you define your data model, using a graphical interface to add entities, attributes, and relationships. Once your model is defined, Xcode can generate NS-managed object subclasses for each entity, which are Objective-C classes that represent your data in code. These subclasses make it easier to access and manipulate your data within Swift, providing type safety and reducing errors. By following these steps, you can quickly integrate core data into your application. Understanding the core concepts of core data is essential for effective data management. A managed object represents a single record in your data model, such as a specific user or product. The managed object context is where all changes to your data occur, acting as a temporary cache that tracks modifications before they are saved. This context also coordinates with the persistent store to ensure data consistency. The persistent store coordinator plays a critical role by managing the connection between the managed object context and the actual storage files. Together, these components form the backbone of core data, enabling efficient and reliable data handling. Performing CRUD operations with core data involves creating, reading, updating, and deleting data records. To create data, you instantiate a managed object from your data model and set its attributes, then save the context to persist the changes. Reading data requires using NSFetchRequest to query the persistent store, allowing you to retrieve specific records based on criteria. Updating involves modifying the attributes of an existing managed object and saving the context again. Finally, deleting data requires removing the managed object from the context and saving the changes. These operations form the foundation of data manipulation in core data, making it a versatile tool for app development. Fetching data with NS fetch request is a fundamental aspect of working with core data. This class allows you to construct queries to retrieve specific data from the persistent store. You can apply filters using predicates to narrow down your results, such as searching for records where a name matches a specific value. Sorting descriptors can be added to organize the fetched data in a particular order. For example, a predicate like name equals John would return all records with the name John. By mastering NS fetch request, you can efficiently retrieve and display data in your applications, ensuring a smooth user experience. Core data supports complex relationships between entities, allowing you to model real-world scenarios effectively. One-to-one relationships connect two entities, where each instance of one entity is linked to exactly one instance of another. One-to-many relationships, such as a customer having multiple orders, enable you to track multiple records from one entity. Many-to-many relationships allow entities to have multiple connections to other entities, such as a user belonging to multiple groups. Core data automatically handles cascading deletes and validation, ensuring that relationships remain consistent and data integrity is maintained. These features make core data a robust solution for managing interconnected data. Validation and constraints are crucial for maintaining data integrity in core data. You can define validation rules directly in the data model, such as setting a minimum or maximum value for an attribute. This ensures that data meets specific criteria before it is saved. For more complex validation, you can override the validate value method in your managed object subclass to implement custom checks. These validations prevent incorrect or incomplete data from being stored, reducing errors, and ensuring that your application's data remains accurate and reliable. By leveraging these features, you can build more robust and trustworthy applications. Optimizing performance in core data is essential, especially when working with large datasets. Batch updates allow you to modify multiple records at once, reducing the overhead of individual operations. Avoiding unnecessary saves of the managed object context helps prevent performance bottlenecks, as each save operation can be resource intensive. Monitoring memory usage by adjusting the managed object context settings, such as using a background context for heavy operations, ensures that your application runs smoothly. These techniques help you maintain a responsive and efficient user experience, even when handling large volumes of data. In conclusion, Core Data is an invaluable tool for managing data persistence in iOS and macOS applications. Its architecture, consisting of data models, managed object contexts, and persistent stores, provides a structured approach to data handling. By mastering CRUD operations, relationships, and performance optimization techniques, you can build efficient and scalable applications. Core Data simplifies complex data management tasks, allowing you to focus on creating innovative features for your users. With practice and understanding, you can harness the full potential of Core Data to enhance your app development workflow. Networking in software development refers to the process of enabling communication between devices, systems, or services over a network. It is essential for applications to exchange data, retrieve resources, or interact with remote servers. In iOS and macOS development, URL session serves as the primary framework for handling network requests. It provides a robust and flexible way to perform tasks like fetching data from APIs, downloading files, or uploading content. Common use cases include retrieving user data from a backend server, fetching images or videos, and synchronizing data between a device and a cloud service. Understanding how to leverage URL session effectively is crucial for building responsive and efficient applications. URL session is Apple's native framework designed for network communication in Swift. It abstracts the complexities of lower-level networking tasks, allowing developers to focus on high-level operations. The framework consists of three key components: URL session, which manages the overall session; URL session task, which represents individual network operations; and URL session configuration, which defines the behavior of the session. URL session supports three main types of tasks: data tasks for retrieving data, download tasks for saving files, and upload tasks for sending data to a server. Each task type is optimized for specific scenarios, ensuring developers can choose the right tool for their needs. To create a URL session, you start by initializing it with a configuration. The default configuration is suitable for most scenarios, but you can also use background configurations for tasks that need to continue even when the app is suspended, or custom configurations to tailor settings like timeout intervals or cache policies. For example, let session equals URL session configuration. Default sets up a session with standard settings. Additionally, you can assign a delegate to handle events like task completion, progress updates, or errors. This is particularly useful for managing complex workflows or long-running tasks that require fine-grained control. Data tasks are used to fetch data from a URL and are commonly employed to retrieve JSON, XML, or other structured data from APIs. The method data task with completion handler initiates a task that downloads data and returns it in a completion handler. Within this handler, you can inspect the response, check for errors, and process the received data. For instance, fetching JSON from a public API, like a weather service, involves parsing the response into a Swift model using Codable. Proper error handling is critical here, as network conditions can vary, and servers may return unexpected results. Download tasks are designed to handle file downloads from a URL, making them ideal for scenarios like fetching images, videos, or large datasets. The method download task with completion handler allows you to specify a destination URL where the file will be saved. This destination can be a temporary location for short-term use, or a persistent one for long-term storage. Additionally, URL session provides delegate methods like URL session, download task, did write data, total bytes written, all bytes expected to write, to monitor download progress, enabling you to update the user interface with real-time feedback. Upload tasks are used to send data from an app to a server, often for actions like submitting forms, uploading files, or sending user-generated content. The method upload task with from completion handler allows you to specify the URL and the data to be sent. When uploading files, it's common to use multi-part /form data encoding to structure the request, which includes both the file and any associated metadata. Secure uploads require setting appropriate headers, such as authentication tokens or content types, and handling SSL TLS to ensure data integrity. This makes upload tasks essential for features like profile picture uploads or document sharing. Handling responses involves interpreting the server's HTTP status codes and validating the data received. Common codes include 200 OK for successful requests, 404 not found for missing resources, and 500 server error for internal issues. URL session provides methods to check these codes and ensure the response is valid. Additionally, you can validate data integrity by verifying content types, checking for redirects, or using delegate methods to handle caching. The URL response object contains metadata about the response, while URL session task delegate methods allow you to customize how the app interacts with the server during the task lifecycle. Error handling is a critical aspect of network programming, as requests can fail due to various reasons like network outages, server errors, or invalid URLs. URL session throws errors that can be caught using Swift's error handling mechanisms. Implementing retry logic, such as exponential backoff, can improve resilience for transient failures. Delegate methods like URL session task did complete with error provide detailed error information, enabling developers to log issues or notify users. Effective error handling ensures the app remains stable and provides a better user experience even when network conditions are unreliable. Best practices for URL session include leveraging Swift's modern concurrency features, like async await, to simplify asynchronous code. Caching responses can significantly improve performance by reducing redundant network requests, which is especially useful for frequently accessed data. Security is paramount, so always use HTTPS to encrypt data in transit, and consider SSL pinning to prevent man-in-the-middle attacks. Additionally, structuring code with clear separation of concerns, such as encapsulating network logic in dedicated classes or functions, enhances maintainability and scalability. Following these practices ensures robust, secure, and efficient network interactions. In summary, URL session is a powerful framework for handling network operations in Swift, offering tools for data fetching, file downloads, and secure uploads. Understanding the different task types and implementing proper error handling ensures reliable communication between apps and servers. By applying best practices like caching, security measures, and modern concurrency, developers can build efficient and user-friendly applications. The key takeaway is to practice integrating URL session with real-world APIs to reinforce these concepts and gain hands-on experience. Testing is an essential practice in software development that ensures the reliability and correctness of code. By writing tests, developers can verify that their code behaves as intended, which is particularly important in complex applications where even small errors can lead to significant issues. Unit tests, which focus on individual components like functions or methods, allow us to isolate and validate specific parts of the code base. This not only improves code quality, but also reduces the likelihood of bugs slipping into production. In the Swift ecosystem, the XC test framework is the go-to tool for writing and running tests, providing a structured and efficient way to implement testing strategies. The XC test framework is Apple's official solution for testing Swift applications. It offers a comprehensive set of tools, including assertions to check conditions, test cases to organize individual tests, and test runners to execute and report results. This framework is deeply integrated into Xcode, making it easy for developers to write, run, and debug tests directly within the IDE. XC test supports multiple test types, such as unit tests for individual functions, integration tests for combined components, and UI tests for user interface interactions. This versatility makes XC test a powerful ally for developers aiming to build robust and maintainable applications. To write unit tests in Swift, developers create a subclass of XC test case, which serves as the foundation for all test classes. Each test method is defined with a function that starts with the word test, such as func test example. This naming convention helps the test runner identify and execute test methods automatically. Within these methods, developers use assertions to validate expected outcomes. For example, XCT assert equal checks if two values are the same, while XCT assert true confirms a Boolean condition. By following this structure, developers can systematically test their code and ensure it meets requirements. assertions are the core of any test suite, allowing developers to verify conditions and ensure correctness. The XCT assert equal function checks whether two values are equal, making it useful for comparing expected and actual results. XCT assert true and XCT assert false are used to validate Boolean conditions, such as whether a function returns a true or false value. XCT assert nil helps confirm that a value is nil, which is critical when dealing with optional types. Finally, XCT fail is a tool for forcing a test to fail, often used during debugging to identify problematic sections of code. These assertions provide a clear and concise way to express test expectations. Test fixtures are methods that prepare and clean up the environment for each test. The setup method runs before every test and is used to initialize data or configure dependencies, ensuring that each test starts with a consistent state. Conversely, teardown executes after each test to release resources or reset variables, preventing unintended side effects between tests. This isolation is crucial for maintaining reliable and repeatable test results. For example, if a test involves a database connection, setup might establish the connection while teardown closes it. By using fixtures, developers can create tests that are independent and easier to manage. Running tests in Swift can be done through various tools. The test navigator in Xcode provides a visual interface to select and execute tests, making it easy to run individual tests or entire test suites. For automation, command line tools like Xcode build allow developers to run tests as part of a build process. Integrating tests into CI/CD pipelines, such as GitHub Actions, ensures that tests are executed automatically with every code change, catching issues early. Xcode's report navigator displays detailed test results, including pass-fail statuses and error messages, helping developers quickly identify and resolve problems. Mocking and stubbing are techniques used to replace real dependencies with simulated ones, enabling tests to focus on specific components without external interference. By using protocols and dependency injection, developers can swap out real objects, such as network clients or databases, with mock versions that mimic their behavior. This is particularly useful when testing code that interacts with external systems, like APIs or file systems, where actual calls might be slow or unreliable. Tools like XC Test Mock or custom stubs help implement these mocks, allowing developers to test edge cases and ensure their code works correctly in isolation. Adhering to best practices in testing ensures that test suites are effective and maintainable. Writing tests for edge cases and critical logic helps uncover hidden bugs that might not be apparent during normal operation. Keeping tests small and focused on a single responsibility makes them easier to read, debug, and update. Automating tests through CI/CD pipelines ensures that every code change is validated consistently, reducing the risk of regressions. Additionally, maintaining high test coverage for key features provides confidence that the application behaves as expected, even as it evolves over time. These practices collectively contribute to a more reliable and scalable code base. In conclusion, testing is a cornerstone of building robust and maintainable Swift applications. The XC test framework provides the tools necessary to implement unit tests, validate code behavior, and ensure reliability. By following best practices such as writing focused tests, using mocking techniques, and integrating tests into CI/CD pipelines, developers can create a culture of quality and continuous improvement, embracing testing as an integral part of the development process not only enhances software quality, but also fosters confidence in the code base, making it easier to innovate and iterate over time. Debugging is an essential skill for any developer working with the Swift programming language. It allows us to identify and fix errors in our code, ensuring that our applications run smoothly and efficiently. In Swift, we have powerful tools at our disposal, such as the Xcode debugger, print statements, and LLDB. These tools help us trace the flow of our programs, inspect variables, and understand the behavior of our code. By mastering these debugging techniques, we can significantly improve the reliability and performance of our applications, making them more robust and user-friendly. One of the simplest yet most effective debugging techniques is using print statements. The print function in Swift allows us to output variable values and track the flow of our program as it executes. For example, we can print the value of a variable at different points in our code to see how it changes over time. Additionally, we can add conditional prints to focus on specific parts of our code. For instance, we might print a message only when a certain condition is met, helping us isolate problematic sections. Swift also provides compiler directives like warning and error, which allow us to insert code-level alerts. These can be useful for marking areas of our code that need attention, or for preventing compilation if a specific issue is present. Another powerful debugging tool is the Xcode debugger, which lets us pause the execution of our code at specific points. By setting breakpoints in Xcode, we can stop the program at a particular line of code and inspect the current state of our application. This includes checking the values of variables, evaluating expressions, and stepping through code line by line. The debugger also allows us to navigate through our code using commands like step over, step into, and step out, giving us a detailed view of how our program operates. Conditional breakpoints are especially useful when we want to pause execution only when a specific condition is true, making it easier to target and diagnose complex issues. For more advanced debugging, Swift developers can leverage LLDB commands, which are part of the command line debugger. The PO command stands for print object and allows us to inspect the contents of Swift objects, such as classes or structures, in detail. The BT command, or backtrace, shows the call stack, helping us understand the sequence of function calls that led to the current point in our code. To navigate through the code, we can use N for next to move to the next line of code, or S for step to enter a function call. If we want to resume execution, the C command, or continue, allows us to proceed until the next breakpoint. These LLDB commands provide a flexible and efficient way to debug complex applications. In addition to print statements and the debugger, Swift offers logging frameworks like OS Log for structured logging in production code. Unlike print statements, which can be overwhelming in large applications, OS Log allows us to log messages with specific severity levels, such as debug, info, or error. This makes it easier to filter and analyze logs in the Xcode console. By examining the console output, we can identify runtime errors, track the flow of our program, and pinpoint the source of issues. Logging with OS Log also enables us to maintain a record of events that occur during the execution of our app. which can be invaluable for troubleshooting and improving performance. Unit testing is another critical approach to debugging in Swift. By writing XC test cases, we can isolate specific parts of our code and reproduce bugs in a controlled environment. This allows us to test individual functions or methods and ensure they behave as expected. The XC test framework provides assertions like XCT assert, which let us validate that a particular condition is true. For example, we can check if a function returns the correct value, or if an error is thrown under certain conditions. Automating these tests ensures that our code remains stable as we make changes, helping us catch regressions early and maintain a high standard of quality. Despite the availability of powerful debugging tools, developers often fall into common pitfalls that can hinder their ability to resolve issues efficiently. One such mistake is overlooking nil values or using force unwrapping, which can lead to runtime crashes if the optional is not properly handled. Another common issue is ignoring compiler warnings or errors, which often point to potential problems in the code. Additionally, failing to reproduce issues in a controlled environment can make it difficult to diagnose and fix bugs. By being mindful of these pitfalls and adopting best practices, we can significantly reduce the time spent debugging and improve the overall quality of our code. In conclusion, debugging is a critical skill for any Swift developer, requiring a combination of tools, techniques, and systematic problem solving. By using breakpoints, LLDB commands, and logging frameworks, we can efficiently identify and resolve issues in our code. Print statements and unit testing also play a vital role in ensuring that our applications are reliable and performant. As we continue to practice and refine our debugging abilities, we become more adept at navigating the complexities of software development and delivering high-quality solutions. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of Swift will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.